Welcome back to Scientific Discovery Hub. Have you ever looked up at the stars and wondered, are we alone? For centuries, this question has captivated humanity. Today we are closer than ever to an answer, not by hunting for aliens, but by studying the faint chemical traces in the atmospheres of distant worlds. In this video, we'll dive into the thrilling science of exoplanet atmospheres and the race to detect biosignatures, molecules that could hint at life beyond Earth. Imagine trying to guess the ingredients of a cake by only smelling the smoke from its oven. That's essentially what scientists do when they analyze exoplanet atmospheres. Using advanced telescopes and clever techniques like the transit method, researchers study starlight filtered through these distant skies to uncover hidden clues. Could oxygen, methane, or water vapor be whispers of alien life? Or are they just cosmic red herrings? We'll break down the tools and discoveries driving this search. Learn how the James Webb Space Telescope is revolutionizing our ability to sniff out alien atmospheres, why ozone might act as both a shield and a warning sign, and how extremophiles on Earth are rewriting our definition of habitable worlds. Along the way, we'll tackle tricky questions. How do we avoid false positives? What if life exists in forms we cannot even imagine? And what happens if we do find it? This journey isn't just about science, it's about philosophy, ethics, and our place in the universe. From the challenges of detecting water worlds to the mind-bending idea of panspermia, life hitchhiking across space, we'll explore what it takes to decode the cosmos. Plus, we'll examine real-world examples like the TRAPPIST-1 system, and discuss how comparing exoplanets to our own solar system helps us avoid biased assumptions. Whether you're a space enthusiast or new to astrophysics, this video will take you from the basics of biosignatures to the cutting-edge tech reshaping our understanding of life's possibilities. So hit play, lean in, and join us as we unravel one of humanity's greatest mysteries. Are we alone in the universe? Don't forget to like, subscribe, and ring the bell for more deep dives into the wonders of science. Together, we're unlocking the secrets of the cosmos, one exoplanet at a time. Let's begin. Beneath the velvet expanse of the night sky, humanity has long been haunted by a question as ancient as consciousness itself. Are we alone? For thousands of years, this query has flickered in the minds of stargazers, philosophers, and poets, shaping cultures and inspiring myths. In the cradle of Sumerian civilization, Babylonian astronomers etched celestial patterns into clay tablets, seeking divine messages in the movements of stars. The Greeks mused about other worlds beyond the moon, while medieval scholars debated whether the heavens held infinite realms teeming with life. Today, as we stand on the precipice of knowledge forged by telescopes and algorithms, the question endures, but now it is no longer confined to myth or speculation. It is a scientific pursuit, a quest to decode the silent symphony of the cosmos. The universe, vast and indifferent, stretches its arms across 93 billion light years, a tapestry woven with galaxies, each containing billions of stars. Among these stars, planets orbit in the shadows of their suns, many hidden from our view. Yet, within the last 3 decades, we have begun to glimpse these distant worlds, exoplanets, and to listen for the faintest echoes of life within their atmospheres. No longer do we seek the familiar silhouette of an alien spacecraft or the hypothetical little green men of popular imagination. Instead, we turn our ears to the chemical language of the cosmos, searching for the subtle imprints left by biology, oxygen, methane, water vapor. These molecules, when found in the right combinations, may whisper of forests swaying under alien winds, of oceans lapping against shores of unknown minerals, or of microbial colonies thriving in the depths of alien seas. This search is not merely an exercise in curiosity. It is a mirror held up to our own existence. To discover life elsewhere would be to affirm that the conditions for life are not unique to Earth, that the universe is a fertile ground for the emergence of complexity. Conversely, to find only silence would not necessarily diminish our significance, but rather deepen our appreciation for the rare and precious nature of our own world. Either outcome would reshape humanity's self-perception, challenging the anthropocentric narratives that have defined our species for millennia. Exoplanets, planets orbiting stars beyond our solar system, are the stage upon which this cosmic drama unfolds. As of today, over 5,000 exoplanets have been confirmed, ranging from scorching super-Earths to gas giants larger than Jupiter. Many of these worlds lie in the so-called habitable zone, a region around a star where temperatures could allow liquid water to exist on a planet's surface. However, habitability is not synonymous with inhabitedness. A planet may possess the right temperature and atmospheric pressure, yet lack the chemical ingredients for life, or worse, harbor conditions that actively suppress it. Thus, scientists have turned to atmospheric chemistry as a more precise indicator of potential life. Biosignatures, the chemical fingerprints of life, are the primary targets of this search. Oxygen, for instance, is highly reactive and would quickly disappear from an atmosphere unless continuously replenished by processes such as photosynthesis. On Earth, plants and algae produce oxygen as a byproduct of converting sunlight into energy, creating a balance that sustains aerobic life. Methane, another reactive gas, is often produced by biological processes such as bacterial metabolism. When oxygen and methane coexist in an atmosphere, their mutual instability suggests a dynamic system, one where life actively maintains their presence. Water vapor, too, is a crucial biosignature, as liquid water is essential for all known forms of life. Together, these gases form a triad of possibility, a chemical harmony that may signal the presence of life. Detecting these biosignatures requires sophisticated technology and meticulous analysis. Astronomers use a technique called transmission spectroscopy to study exoplanet atmospheres. When a planet transits its star passing between the star and Earth, starlight filters through the planet's atmosphere. By analyzing the spectrum of this light, scientists can identify which wavelengths are absorbed by atmospheric gases. Each gas has a unique spectral fingerprint, a pattern of absorption lines, that reveals its presence. For example, oxygen absorbs light in the near-infrared range, while methane leaves its mark in the visible and infrared. The James Webb Space Telescope, JWST, launched in 2021, is equipped with instruments designed to detect these faint signals, peering into the atmospheres of exoplanets with unprecedented precision. Yet the task is fraught with challenges. False positives abound. Methane, for instance, can be produced by geological processes such as volcanic activity, and oxygen can accumulate in an atmosphere through non-biological means, such as the photodissociation of carbon dioxide. Distinguishing between biogenic and abiotic sources requires careful modeling and contextual clues. For example, the presence of ozone, a molecule formed when oxygen molecules are split by ultraviolet light, could indicate a biologically active oxygen cycle. Similarly, the detection of disequilibrium chemicals that should not coexist under normal conditions may point to life's influence. The search is further complicated by the sheer distance of these worlds. Even the nearest exoplanets are tens of light years away, meaning the light we observe was emitted centuries ago. The data we collect is a snapshot frozen in time, a fleeting glimpse into a distant epoch. The discovery of a biosignature-rich exoplanet would send shockwaves through science, philosophy, and society. Imagine a day when astronomers announce the detection of oxygen and methane in the atmosphere of a rocky world orbiting Proxima Centauri, our closest stellar neighbor. The implications would ripple outward, challenging long-held assumptions about life's uniqueness and humanity's place in the cosmos. If life exists elsewhere, it would suggest that the emergence of biology is not a fluke, but a natural consequence of the universe's laws. Such a revelation would rekindle the Copernican principle, the idea that Earth is not privileged in the universe, while simultaneously deepening our awe at the conditions that made life possible here. However, the implications extend beyond science. Theological perspectives would be forced to confront new realities. Would a God who created the universe also have sown life across the stars? Could the concept of humanity's special status in creation be reconciled with the existence of alien life? These questions would spark debates not only among theologians, but also within religious communities, as faith traditions adapt to a universe teeming with life. Meanwhile, existential questions would arise for individuals. If we are not alone, what does it mean to be human? Is our identity tied to being the sole intelligent species, or can we embrace a broader sense of belonging to a cosmic family? even the absence of detectable life would carry profound meaning. After decades of searching, if no biosignatures were found, it might suggest that life is exceedingly rare, a cosmic lottery won only once, on Earth. This outcome would reinforce the importance of preserving our planet and its ecosystems, recognizing that life may be fragile and finite. Alternatively, it might prompt a re-evaluation of our methods. Perhaps we are looking for the wrong biosignatures, or perhaps life takes forms we cannot yet imagine, entities based not on carbon but on silicon, or thriving in environments we consider inhospitable. The search for extraterrestrial life is not merely about finding answers, but about refining our understanding of what life is and how it might manifest under diverse conditions. The emotional weight of these possibilities cannot be overstated. The prospect of discovering life, even microbial, would inspire a sense of unity among humans. In the face of the vast unknown, we would share a common destiny to explore, to understand, and to connect with whatever else exists in the universe. Conversely, the realization that we might be alone could evoke both humility and determination. It would remind us that Earth is our only home, a fragile oasis in an otherwise desolate expanse, urging us to protect it with greater care. Either way, the search for life beyond Earth compels us to look inward, as well as outward, to examine our values, our curiosity, and our capacity for wonder. To unravel the mysteries of exoplanet atmospheres, we must first master the art of seeing the unseen. The faint chemical whispers of distant worlds are hidden within the glare of their stars, drowned in the noise of cosmic radiation and instrumental limitations. Yet humanity has always excelled at pushing the boundaries of perception, inventing tools that extend our senses to realms once thought inaccessible. From Galileo's rudimentary telescope to the James Webb Space Telescope's infrared eyes, our journey to decode the cosmos has been one of relentless innovation. In the next segment, we will delve into the tools that allow us to pierce the veil of interstellar darkness and glimpse the atmospheres of exoplanets. We will explore the evolution of telescopic technology, from the earliest optical instruments to the cutting-edge spectrometers and coronagraphs that enable modern astronomy. Along the way, we will uncover the ingenuity behind techniques such as direct imaging, radial velocity measurements, and microlensing, each a testament to human creativity in the face of cosmic adversity. Understanding these tools is not merely an academic exercise. It is the foundation upon which our search for life rests. Without the ability to observe, we cannot hope to comprehend. And so, with instruments as our eyes and curiosity as our compass, we venture forward into the unknown, guided by the promise of discovery. In the vast, silent expanse of the cosmos, where stars burn like distant lanterns and galaxies spiral in slow, eternal waltzes, the task of discovering new worlds seems almost impossibly grand. Yet, humanity's ingenuity has devised a method so delicate and profound that it can discern the faintest flicker in a star's light, a flicker caused by a planet, no larger than Earth, passing across its face from thousands of light years away. Imagine, if you will, a single firefly darting past the blinding glare of a car's headlights. Its presence is fleeting, its effect imperceptible to the naked eye. Yet with the right tools, the subtle dimming of the headlights could betray the firefly's path. This is the essence of the transit method, a technique that transforms the ephemeral dance of light into a map of alien worlds. The universe, in its infinite scale, often hides its secrets in the quietest signals. A planet's shadow, cast across a star, is one such signal, a whisper in the noise of celestial light. To detect this, astronomers must peer through the veil of space with instruments capable of measuring changes in brightness as minute as 0.01%. Such precision is akin to spotting a moth fluttering across the face of a lighthouse from miles away. Yet this is precisely what the transit method achieves, leveraging the interplay of geometry, physics, and patience to unveil the hidden architecture of planetary systems. It is a testament to human curiosity, a bridge between the observable and the unknown, where every dip in a star's light carries the promise of discovery. This method is not merely a tool, but a philosophical lens, reframing our place in the cosmos. When we observe a transit, we witness not just the shadow of a planet, but the intricate choreography of orbital mechanics, the gravitational tides shaping the fates of stars and worlds alike. In those moments, the universe reveals its patterns, not as chaos, but as a grand design etched in light and shadow. And in that revelation lies the thrill of the transit method, the ability to see the unseen, to read the cosmic script written in the flickers of distant stars. At its core, the transit method relies on the alignment of three celestial actors: a star, a planet, and the observer. When a planet passes directly between its host star and Earth, it blocks a fraction of the star's light, creating a temporary eclipse. This dip in brightness, though minuscule, is measurable with modern telescopes. The depth of the dip corresponds to the ratio of the planet's size to the star's size. For instance, a Jupiter-sized planet orbiting a Sun-like star might obscure about 1% of its light, while an Earth-sized world would dim it by less than 0.01%. Detecting such a subtle change demands instruments with extraordinary sensitivity, such as NASA's Kepler Space Telescope or the transiting Exoplanet Survey satellite TESS. These machines monitor thousands of stars simultaneously, sifting through data for the telltale signature of a transit. But the transit method offers more than just the size of a planet. As starlight filters through the planet's atmosphere during the transit, certain wavelengths are absorbed by atmospheric gases, leaving behind spectral fingerprints. By analyzing these fingerprints, scientists can deduce the composition of the planet's air. Oxygen, water vapor, methane, and carbon dioxide each leave distinct imprints, revealing whether a world is shrouded in clouds, cloaked in methane, or potentially hospitable to life. This technique, known as transmission spectroscopy, turns the act of observation into a chemical dissection of alien skies. However, the transit method is not without its challenges. First, the alignment must be nearly perfect. The planet's orbit must be inclined just right so that, from our vantage point, it passes directly in front of the star. If the orbit is tilted by even a few degrees, the transit would never occur, rendering the method ineffective. Second, the rarity of transits for long-period planets complicates detection. A planet with an Earth-like year would only cross its star once per year, requiring decades of continuous observation to confirm its existence. Finally, false positives, such as eclipsing binary stars or instrumental noise, can mimic the signal of a planet, necessitating rigorous follow-up studies with complementary techniques like radial velocity measurements. Despite these hurdles, the transit method has proven to be a cornerstone of exoplanet science. Its power lies in its simplicity and scalability, allowing astronomers to survey vast swaths of the sky and catalog thousands of worlds. Each detected transit is a puzzle piece in the mosaic of planetary diversity, illuminating the myriad ways nature constructs its celestial creations. Since the dawn of the transit method, it has revolutionized our understanding of planetary systems. Over 5,000 confirmed exoplanets have been discovered using this technique, each one expanding the boundaries of what we consider possible. Among these worlds are gas giants with scorching temperatures, rocky super-Earths teeming with volcanic activity, and enigmatic mini-Neptunes shrouded in thick, hydrogen-rich atmospheres. These discoveries have shattered preconceived notions about planet formation, revealing that our solar system is but one variation in a cosmic menagerie. Yet the transit method carries inherent biases that shape the types of planets it uncovers. Large planets orbiting close to their stars, often dubbed hot Jupiters, are the easiest to detect because they block more light and transit more frequently. Smaller, Earth-like worlds in the habitable zone, where liquid water might exist, remain stubbornly elusive. Their transits are fainter and rarer, requiring exceptionally stable instruments and years of patient observation. Does this scarcity reflect their true rarity in the universe, or simply the limits of our current technology? The answer may lie in upcoming missions like the James Webb Space Telescope, JWST, or the European Space Agency's Plato satellite, which aim to push the boundaries of detection. The question of Earth-like planets is particularly profound. Are they common, scattered like seeds in the galactic soil, or rare, isolated jewels in the void? Statistical models suggest that small planets are abundant, but their detection demands a confluence of luck and innovation. Consider the case of TRAPPIST-1, a system of 7 Earth-sized planets orbiting a nearby red dwarf star. Their tight configuration made transits frequent and detectable, offering a glimpse into a potentially habitable neighborhood. Yet such systems are exceptions rather than the rule, underscoring the need for improved observational strategies. Even as we grapple with these limitations, the transit method continues to inspire. Every newly discovered planet adds a thread to the cosmic tapestry, weaving together stories of formation, evolution, and survival. It reminds us that the universe is a realm of surprises, where even our most advanced tools reveal only fragments of its grandeur. And in those fragments, we glimpse the possibility of worlds unlike our own. Worlds that may one day teach us what it truly means to be alone in the cosmos. As the transit method unveils the silhouettes of distant worlds, it also opens a portal to deeper mysteries. The planets it discovers are not mere shadows, but dynamic spheres, each with its own history and potential. Among the most tantalizing clues hidden in their atmospheric spectra is the presence of oxygen, a gas so familiar to us yet profoundly enigmatic in its cosmic context. On Earth, oxygen is a byproduct of life, a silent testament to the breadth of forests, oceans, and ancient photosynthetic organisms. Could its detection on another world signal a similar story of biological emergence? Or might it arise through non-biological processes, casting doubt on its significance? The search for oxygen and other biosignatures represents the next frontier in our quest to understand the universe. With the transit method as our guide, we stand on the precipice of this discovery, poised to decode the chemical signatures of alien atmospheres. In the coming segment, we will delve into the nature of oxygen as a biosignature, exploring its origins, its role in planetary evolution, and the challenges of interpreting its presence. For in the dance of light and shadow, we may yet find the first whispers of life beyond Earth. This script adheres to the requested structure and tone, blending scientific detail with a contemplative narrative. Each section builds upon the previous, emphasizing the transit method's role in unraveling cosmic mysteries while setting the stage for the next topic. The language is enriched with metaphors and analogies to evoke wonder, ensuring the script remains both informative and engaging. The air we breathe is not merely a convenience of earthly existence. It is a testament to the planet's living history. Oxygen, the invisible force that sustains us, pulses through every breath, a silent promise of life's enduring presence. Yet, if we peer beyond our home world, the story of oxygen becomes far more enigmatic. To an alien astronomer scanning the cosmos, a distant exoplanet shrouded in oxygen-rich clouds might seem like a beacon of possibility, a world teeming with forests, oceans, and creatures exchanging their own silent whispers of survival. But such a reading would be perilously simplistic. For oxygen, the very element that defines Earth's vitality, is also a master of deception. It is a ghost that can haunt planetary atmospheres without the presence of life, conjured by the cold alchemy of starlight and chemistry. In the grand theater of the universe, oxygen's presence demands not celebration, but scrutiny. Is it a herald of life, or a mirage born of indifferent physics? This question lies at the heart of our search for extraterrestrial worlds, capable of harboring life, a quest that hinges on deciphering the subtle language of planetary atmospheres. To understand oxygen's duality, we must first retrace its origins on Earth. For most of our planet's 4 billion-year history, oxygen was a rare and fleeting molecule, bound tightly in rocks and minerals rather than free in the air. The Great Oxidation Event, a cataclysmic shift around 2.4 billion years ago, transformed Earth from a world of anaerobic gloom into one where oxygen began to dominate. This transformation was not the work of geological forces, but of life itself, specifically the relentless labor of cyanobacteria, microscopic architects, who harnessed sunlight to split water and release oxygen as a byproduct. Over eons, their collective efforts flooded the atmosphere with a gas so reactive that it corroded the planet's crust, reshaped ecosystems, and ultimately paved the way for complex life. Today, Earth's oxygen is sustained by the same process, photosynthesis, the green engine of life, continuously recycling the air we depend on. Yet this intimate relationship between oxygen and biology does not guarantee that all oxygen in the universe signals life. Consider a barren world bathed in the unrelenting radiation of its star. Here, ultraviolet photons could tear apart water vapor in the upper atmosphere, freeing hydrogen atoms to escape into space while leaving behind molecular oxygen. Such a process, devoid of life, could mimic the fingerprints of a biologically active planet. The challenge for astrobiologists is to distinguish between these two scenarios, to pass the difference between oxygen produced by the quiet hum of cellular respiration and that conjured by the violent symphony of stellar radiation. This distinction is not merely academic, it is the linchpin of our ability to recognize life beyond Earth. As we venture further into the cosmos, oxygen remains both a guidepost and a riddle. Its abundance can illuminate the path toward habitable worlds, yet it can also lead us astray, whispering promises of life where none exists. To navigate this ambiguity, we must look beyond single molecules and immerse ourselves in the intricate tapestry of planetary atmospheres, seeking the patterns that reveal the hand of life, or the absence thereof. In doing so, we confront the profound humility of our own perspective, that even the most familiar elements can become strangers when viewed through the lens of the unknown. The story of oxygen begins with a paradox. It is both a product of life and a potential illusion. On Earth, the dominance of oxygen in our atmosphere is a direct consequence of biology. Every breath we take is a continuation of a process initiated by ancient microbes. These cyanobacteria, thriving in primordial seas, converted carbon dioxide and water into sugars, releasing oxygen as a waste product. At first, this oxygen reacted with iron in the oceans and crust, forming rust-colored banded iron formations. Only after these reservoirs were saturated did oxygen begin to accumulate in the atmosphere, triggering the Great Oxidation Event. This transition was not gentle. It poisoned many anaerobic species and reshaped the planet's chemistry. Yet it also laid the foundation for aerobic life, the diverse array of organisms, including humans, that rely on oxygen to extract energy from food. Without life, however, oxygen is a transient guest. It is highly reactive, prone to binding with other elements in a relentless quest for stability. On a lifeless world, any oxygen produced would swiftly vanish, consumed by oxidation reactions that transform it into oxides of carbon, sulfur, or nitrogen. For instance, in the absence of photosynthesis, oxygen would combine with methane, a potent greenhouse gas, to form carbon dioxide and water. This rapid disappearance is why Earth's oxygenated atmosphere is an anomaly in the solar system. Mars, for example, has a thin atmosphere dominated by carbon dioxide, with trace amounts of oxygen that are constantly being stripped away by the solar wind. Venus, though rich in carbon dioxide, lacks significant oxygen, its surface instead cloaked in volcanic rock that has absorbed any traces of the element. Yet our biotic processes can generate oxygen under specific conditions. One such mechanism is photodissociation, where high-energy ultraviolet photons from a star collide with water molecules in a planet's upper atmosphere, splitting them into hydrogen and oxygen. The lighter hydrogen atoms escape into space, while the heavier oxygen lingers, accumulating as molecular O2. This process is well documented in the atmospheres of icy moons like Europa and Enceladus, where water plumes interact with radiation. Similarly, on planets lacking a protective magnetic field, the solar wind can strip hydrogen from water molecules, leaving oxygen behind. These scenarios demonstrate that oxygen is not an exclusive signature of life. It is a byproduct of cosmic chemistry, shaped by the interplay of light, heat, and planetary dynamics. To discern whether oxygen on an exoplanet is biologically derived or abiotically produced, scientists must analyze the broader atmospheric context. Oxygen alone is insufficient. It is the relationships between gases that reveal the truth. For example, if a planet exhibits oxygen alongside methane, CH2, this combination is highly improbable without life. Methane and oxygen are chemical adversaries. They react to form carbon dioxide and water, decaying within tens of thousands of years in the absence of a continuous supply. On Earth, methane is continually replenished by biological processes like microbial metabolism and plant decomposition. If an exoplanet possesses both gases in equilibrium, it suggests an active, life-sustaining system at work. Conversely, a planet with oxygen but no methane might indicate a sterile world, where oxygen persists only through abiotic mechanisms and lacks the stabilizing influence of life. This nuanced approach to atmospheric analysis mirrors the detective work of ancient astronomers who sought to decode the heavens. Just as Galileo's telescope revealed moons orbiting Jupiter, challenging the notion of Earth's centrality, modern spectroscopy allows us to peer into the atmospheres of distant worlds. Instruments like the James Webb Space Telescope, JWST, will soon provide unprecedented data, measuring the ratios of gases in exoplanetary atmospheres and identifying spectral lines that betray their presence. By combining these observations with models of planetary chemistry, scientists can begin to untangle the web of possibilities, distinguishing between the whispers of life and the echoes of cosmic processes. Yet the task is fraught with uncertainty. Planets vary dramatically in size, temperature, and geological activity, factors that influence the rates of gas production and destruction. A super-Earth with intense volcanism might release oxygen through outgassing, mimicking the signatures of a biologically active world. Similarly, a planet with a thick atmosphere rich in nitrogen could dilute the concentrations of oxygen and methane, making their coexistence harder to detect. These complexities underscore the need for caution in interpreting data. As Carl Sagan once cautioned, extraordinary claims require extraordinary evidence, a principle that guides the search for extraterrestrial life, ensuring that we do not mistake the noise of the universe for the voice of another civilization. The interplay of oxygen and methane in planetary atmospheres is a dance of fragility and precision, a tenuous balance that reveals the hidden rhythms of a world. On Earth, this balance is maintained by the ceaseless churn of life. Photosynthesis generates oxygen, while methane is released by decomposing organic matter, wetlands, and microbial communities. These two gases coexist in a state of dynamic equilibrium, neither dominating nor annihilating the other. Their coexistence is not a coincidence but a result of life's ability to regulate and sustain itself. If we were to observe this balance from afar, we might interpret it as a signal, a Morse code of habitability flashing across the void. Yet the same cannot be said for every world that bears these gases. The presence of oxygen and methane together is a powerful indicator of life, but it is not infallible. Misreading their signals could lead us to embrace false hopes or overlook promising candidates. Consider a hypothetical exoplanet orbiting a red dwarf star, its atmosphere thick with oxygen and methane. At first glance, this might seem like a triumph for astrobiology, a world where the conditions for life appear to align. However, closer inspection might reveal a different story. Red dwarfs emit intense ultraviolet flares that could drive photochemical reactions, splitting water molecules and generating oxygen without the need for life. Simultaneously, geological processes such as serpentinization, a reaction between water and mantle rock, could produce methane abiotically. In this scenario, the planet's atmosphere mimics the signatures of life while remaining sterile. Such false positives highlight the need for a multidimensional approach to atmospheric analysis, one that considers not only the presence of gases but also their abundances, distributions, and interactions with other elements like nitrogen, argon, and ozone. The risks of misinterpretation are compounded by the sheer diversity of planetary environments. Take Mars, a world that once held liquid water and may have supported microbial life. Despite its ancient history of water and potential habitability, Mars today is a desiccated wasteland, its atmosphere dominated by carbon dioxide. Trace amounts of methane have been detected in its thin air, but their origin remains a subject of debate. Some scientists argue that the methane is the result of abiotic processes like the breakdown of organic compounds by radiation or the slow release from clathrate deposits. Others propose that it could be a vestige of ancient life, trapped in the planet's regolith and occasionally liberated by seismic activity. The ambiguity of Mars methane underscores the difficulty of drawing conclusions from isolated data points. Without additional evidence such as isotopic signatures that distinguish between biological and geological sources, or direct sampling of surface materials, Any interpretation remains speculative. The stakes of this ambiguity are magnified when considering the search for life in the habitable zones of other stars. The habitable zone, often dubbed the Goldilocks region, is defined as the range of distances where a planet could maintain liquid water on its surface. While this concept provides a useful starting point, it is not a guarantee of habitability. A planet within this zone could possess a runaway greenhouse effect, like Venus, or a frozen surface like Enceladus, despite its proximity to a star. Moreover, the habitable zone is a static model, failing to account for the dynamic evolution of planetary systems. A planet that once lay in the habitable zone might now be too hot or too cold, while another might migrate into favorable conditions over time. These variables complicate the search for life, requiring scientists to consider not only a planet's location, but also its history and future trajectory. The discovery of oxygen and methane in tandem could also challenge our assumptions about the forms life might take. On Earth, life is carbon-based, relying on DNA and RNA as genetic material and water as a solvent. But the universe is a crucible of chemistry, and alternative biochemistries remain a tantalizing possibility. Could life exist without oxygen, perhaps in the methane lakes of Titan, where hydrocarbons serve as solvents and exotic molecules play the roles of DNA and proteins, or in the crushing depths of Europa's subsurface ocean, where pressure and darkness foster life forms adapted to extreme conditions? If such life exists, it may leave behind entirely different atmospheric signatures, rendering oxygen and methane irrelevant as biosignatures. This realization forces us to broaden our perspective, recognizing that the search for life is not merely a hunt for familiar markers but an exploration of the unknown. Despite these uncertainties, the pursuit of oxygen and methane as biosignatures remains a cornerstone of modern astrobiology. These gases, when found together in the right proportions, offer a compelling case for habitability. They are not definitive proof of life, but they are a starting point, a hypothesis that can be tested and refined with further observations. The James Webb Space Telescope, set to revolutionize our understanding of exoplanetary atmospheres, will play a pivotal role in this endeavor. By analyzing the light passing through a planet's atmosphere during a transit, JWST can detect the spectral fingerprints of oxygen, methane, and other gases. These measurements will provide critical insights into the chemistry of distant worlds, helping to identify those worthy of deeper study. Yet the quest for life beyond Earth is as much philosophical as it is scientific. Each new discovery forces us to confront the limits of our knowledge and the biases inherent in our search. Are we prepared to accept life that defies our expectations? Can we distinguish between the products of biology and the artifacts of chemistry? These questions echo the age-old human struggle to define our place in the cosmos. The answer may lie not in a single molecule, but in the interplay of countless factors: the tilt of a planet's axis, the composition of its core, the rhythm of its seasons. In this grand cosmic puzzle, oxygen and methane are but two pieces, fragments of a larger narrative waiting to be assembled. As we step back from the luminous thread of oxygen, we find ourselves drawn toward another enigmatic player in the celestial drama, methane. Where oxygen whispers of life's breath, methane murmurs of processes both ancient and elusive. Its presence in a planetary atmosphere adding layers of complexity to the story we seek to unravel. Unlike oxygen, which is a fleeting guest without life stewardship, methane is a molecule of paradoxes. It is a greenhouse gas of formidable potency, capable of trapping heat and shaping a planet's climate. Yet it is also fragile, susceptible to destruction by sunlight and chemical reactions. On Earth, methane is a byproduct of life's hidden workings: microbial fermentation in swamps, the digestive systems of ruminants, and the decay of organic matter. But it is also forged by the slow grinding of rock and the seepage of deep earth reservoirs, a reminder that the line between biotic and abiotic is rarely clear. The interplay between oxygen and methane is a delicate balancing act, a cosmic tightrope that reveals the hand of life or the blind forces of chemistry. When these two gases coexist in a stable equilibrium, it suggests a system actively regulated by biological processes. Yet, as we have seen, their presence alone is not enough to confirm life. To disentangle the threads of their origin, we must delve into the intricate web of planetary chemistry, examining the rates of production and destruction, the influence of stellar radiation, and the geological history of the world in question. This pursuit leads us to the next chapter in our exploration, the methane mystery. How does this molecule, so intimately tied to Earth's biosphere, behave in the vast alien landscapes of exoplanets? Can it serve as a reliable beacon of life, or will it too prove to be a deceptive specter? The answers await as we turn our gaze toward the methane-laden skies of distant worlds, where the dance of molecules may yet hold the key to our cosmic solitude or our long-awaited kinship. In the grand orchestra of the cosmos, where stars hum in the ultraviolet and galaxies spiral in silent harmony, there exists a humble molecule that carries the scent of life itself, methane. Often dismissed as Earth's pungent cousin in the biosignature family, methane, CH*, is a curious alchemist, weaving together carbon and hydrogen in a simple yet profound union. Its faint, acrid odor, a byproduct of ancient microbial metabolisms, has long been a whisper of Earth's own evolutionary story, a testament to the primordial stew that birthed life. Yet, as our gaze extends beyond the cradle of our homeworld, methane transforms from a familiar stench into an enigmatic beacon, a potential herald of alien life hidden in the shadows of distant worlds. This molecule, so abundant in the methane lakes of Saturn's moon Titan and the thin veil of Mars's atmosphere, holds the power to bridge the chasm between the known and the unknown. To unravel its mysteries is to peer into the very essence of what it means to live and to seek in the cold, indifferent void of space. But methane is no mere passive messenger. It is a player in a cosmic game of deception. Its presence in a planet's atmosphere can arise not only from the breath of living organisms, but also from the fiery convulsions of volcanoes, or the slow, grinding dance of tectonic plates. On Earth, it is the workhorse of anaerobic bacteria, a gas exhaled by marshes and belched by cattle. Yet on Mars, its intermittent appearances have sparked debates that echo across the scientific community. Is it a fleeting trick of the light, a statistical anomaly, or the first flicker of life's shadow on a rust-colored world? The answer lies buried in the delicate balance between biology and geology, a balance as fragile as the thin line separating life from its inanimate twin. As we venture further into the habitable zones of exoplanets, where starlight warms alien soils and oceans may shimmer beneath foreign skies, methane becomes both a promise and a puzzle. It is here, in these uncharted realms, that we must learn to listen, not just with instruments but with the humility of seekers who understand that the universe does not always speak in human terms. To study methane is to engage in a dialogue with time itself. On Earth, its role in the Great Oxidation Event, when ancient microbes flooded the atmosphere with oxygen and methane, forever altering the planet's chemistry, reminds us that life has always been a force of transformation. Today, as we scan the skies for the ghostly fingerprints of this molecule, we are not merely searching for a sign of life. We are attempting to decode the language of existence across eons of cosmic evolution. The stakes are high, for every detection brings the tantalizing possibility of companionship in the vast dark, while every false lead serves as a humbling reminder of the universe's penchant for ambiguity. And yet, it is precisely this ambiguity that fuels our curiosity, compelling us to refine our tools, sharpen our minds, and expand the boundaries of what we know. In the end, methane is more than a biosignature. It is a mirror, reflecting our deepest hopes and our most profound uncertainties. Methane's dual identity, as both a product of life and a byproduct of geological activity, is rooted in the intricate chemistry of planetary systems. On Earth, the molecule is predominantly generated by biological processes, particularly the metabolism of methanogenic archaea, single-celled organisms that thrive in oxygen-free environments such as swamps, ruminant stomachs, and deep-sea sediments. These microbes, often dubbed the ancient alchemists of the biosphere, convert carbon dioxide and hydrogen into methane through a process called methanogenesis, releasing the gas as a metabolic waste product. This biological origin accounts for approximately 60% of Earth's methane emissions, with the remaining 40% stemming from geological sources like volcanic eruptions, hydrothermal vents, and the decomposition of organic matter buried deep within the crust. The interplay between these two mechanisms creates a dynamic equilibrium, with methane cycling through the atmosphere, oceans and biosphere in a delicate dance that sustains the planet's climate and ecosystems. Yet this balance is far from static. Methane's short atmospheric lifetime, averaging around 9 years before it is oxidized into carbon dioxide and water vapor, means that its abundance is highly sensitive to changes in both biological productivity and geological activity. On Earth, this sensitivity has led to dramatic shifts in the planet's history. During the Archean Eon, roughly 4 billion years ago, methane likely played a pivotal role in maintaining Earth's warmth under a faint young sun. Without the greenhouse effect of methane and other gases, liquid water might never have persisted, and life itself could have remained trapped in the primordial soup. Later, during the Great Oxidation Event, the rise of oxygen-producing cyanobacteria disrupted the methane cycle, triggering a cascade of chemical reactions that reduced atmospheric methane levels and ushered in a new era of aerobic life. This turbulent history underscores the molecule's role, not just as a biosignature, but as a driver of planetary evolution. The same duality that defines methane on Earth becomes a source of intrigue and contention when applied to other worlds. Take Mars, for instance. Since the early 2000s, multiple spacecraft have detected transient spikes of methane in the Martian atmosphere, some as high as 45 parts per billion. These fluctuations defy explanation, as Mars lacks active plate tectonics and surface water to sustain the geological processes that produce methane on Earth. Volcanic activity, once thought to be a potential source, appears to be dormant or non-existent, leaving scientists to grapple with a paradox. If Mars cannot generate methane today, where does it come from? One hypothesis posits that subsurface reservoirs of ancient methane, trapped in ice-like structures called clathrates, occasionally release the gas through seismic activity or meteorite impacts. Another, more provocative idea suggests that methane could be the product of extant microbial life burrowing deep beneath the planet's icy crust. Both scenarios are plausible, yet neither provides a definitive answer. The challenge lies in disentangling the signal of life from the noise of geological processes, a task complicated by the absence of direct samples from the Martian surface. The conundrum deepens when we turn our gaze to exoplanets, where methane may serve as a key indicator of habitability in the search for life beyond our solar system. Astronomers rely on spectroscopic analysis to detect the unique absorption signatures of molecules in a planet's atmosphere. Methane, with its distinct spectral lines in the near-infrared range, is a prime target. However, its interpretation is fraught with uncertainty. On Earth, methane and molecular oxygen, O2, coexist in a precarious balance as the two react rapidly in the presence of sunlight. Their simultaneous presence in an exoplanet's atmosphere could suggest a stable, life-sustaining environment, what astrobiologists call a Goldilocks scenario. Too much methane, though, might indicate non-biological sources, such as volcanic outgassing, or the breakdown of organic compounds by stellar radiation. Conversely, trace amounts of methane alongside oxygen could hint at a thriving biosphere, where life continuously replenishes the gas despite its tendency to degrade. This complexity is exemplified by the case of GJ 1132b, a rocky exoplanet located 39 light-years from Earth. Initial studies suggested the presence of a thick, methane-rich atmosphere, raising hopes of a potentially habitable world. Subsequent observations, however, revealed that the planet's proximity to its host star, receiving 18 times more radiation than Earth, likely strips away any volatile compounds, rendering methane an unlikely prospect. Such findings underscore the necessity of contextual understanding in astrobiology. A molecule's presence alone is insufficient. Its abundance, distribution, and interaction with other atmospheric components must all be considered. Moreover, the assumption that life elsewhere would follow Earth's biochemical pathways is a dangerous one. Alien organisms might metabolize methane in ways we cannot yet fathom, or they might thrive in conditions entirely inhospitable to terrestrial life. Thus, the search for methane is not merely an exercise in detection, but a call for intellectual humility, a recognition that our own planet's chemistry is but one thread in the vast tapestry of cosmic diversity. The detection of methane on a rocky exoplanet within the habitable zone a region where temperatures allow for liquid water to exist, would be a moment of profound significance, akin to the first spark of a fire in the dark. Such a discovery would ignite a cascade of scientific inquiry, philosophical debate, and perhaps even existential reckoning. Imagine a world orbiting a red dwarf star, its atmosphere tinged with the faintest traces of methane, mingling with water vapor and carbon dioxide. To the untrained eye, it might seem like a mundane combination of gases, but to astrobiologists, it would be a Rosetta Stone, a key to unlocking the secrets of life's universality. Yet, as with Mars, the challenge lies in distinguishing between a genuine biosignature and a clever mimic. How can we ensure that the methane we observe is indeed the product of life, rather than the result of geological trickery or chemical serendipity? One approach is to look for multiple biosignatures in concert, a strategy inspired by Earth's own complex biosphere. On our planet, methane rarely exists in isolation. It is part of a larger network of chemical interactions involving oxygen, nitrogen, and sulfur compounds. For example, the presence of methane alongside ozone, a molecule formed when oxygen reacts with ultraviolet light, could provide a stronger case for biological activity. Ozone is notoriously difficult to produce through non-biological means, making its coexistence with methane a powerful indicator of a living system. Similarly, the detection of nitrous oxide, N2O, or ammonia, NH4, both potent byproducts of microbial metabolism, could reinforce the case for life. This multi-gas approach mirrors the way we diagnose diseases on Earth, where a single symptom is rarely enough to confirm a condition. By seeking patterns, rather than isolated anomalies, we increase the likelihood of identifying true biosignatures and reduce the risk of false positives. However, this method is not without its limitations. Earth-centric assumptions may blind us to alternative biochemistries that could thrive under different environmental conditions. Consider the hypothetical case of a planet with an atmosphere rich in hydrogen and helium, where life forms might metabolize methane instead of producing it. In such a scenario, the presence of methane would not be a biosignature but a baseline condition of the planet's chemistry. To avoid this pitfall, we must remain open to the possibility that life elsewhere may operate on principles alien to our own. Recent studies of extremophiles on Earth, organisms that flourish in conditions previously deemed uninhabitable, offer a glimpse into this possibility. For instance, some archaea in hydrothermal vents produce methane under high pressure, low oxygen conditions, while others consume it in the absence of oxygen. If similar metabolic diversity exists on other worlds, our criteria for detecting life may need to be expanded to include a broader array of chemical signatures. The implications of finding methane-driven life extend beyond the scientific realm, touching on the very nature of our existence. If methane-based organisms exist on exoplanets or moons like Titan, it would challenge our anthropocentric view of life as a phenomenon uniquely tied to water and carbon. It would force us to reconsider the fundamental building blocks of biology and the adaptability of life in the face of extreme environments. Furthermore, such a discovery would reshape our understanding of the universe's potential to harbor intelligence. Would methane-based life forms develop technologies? Could they communicate across the vast distances of space? These questions, while speculative, are essential to the ongoing dialogue about humanity's place in the cosmos. They remind us that the search for extraterrestrial life is not merely an academic pursuit, but a deeply human endeavor, driven by our innate desire to find kinship in the stars. Yet, for all its promise, methane remains a double-edged sword. Every detection is a step forward, but every false lead is a sobering reminder of the universe's indifference to our hopes. The history of science is replete with instances where promising signals were later revealed to be artifacts of flawed instrumentation or misinterpreted data. The Great Red Spot of Jupiter was once thought to be a storm system, while the face on Mars turned out to be a trick of lighting. In the context of astrobiology, these cautionary tales underscore the importance of rigorous verification and interdisciplinary. No single discovery should be taken at face value. Instead, each claim must be scrutinized through the lens of multiple disciplines, from planetary science and chemistry to statistics and philosophy. Only by adopting a holistic approach can we hope to navigate the labyrinth of uncertainty that surrounds the search for life. As we refine our methods and expand our observational capabilities, The role of methane in the quest for alien life will continue to evolve. Future telescopes, such as the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, will enable us to probe the atmospheres of Earth-sized exoplanets with unprecedented precision. These instruments will not only detect methane, but also measure its isotopic composition, providing clues about its origin. For example, biological processes tend to favor lighter isotopes of carbon, while geological activity produces a more uniform mix. By analyzing these subtle differences, we may be able to distinguish between a living and a lifeless world with greater confidence. Additionally, advances in machine learning and artificial intelligence could revolutionize the way we interpret spectral data, allowing us to identify patterns that elude human perception. Despite these technological strides, the ultimate goal remains unchanged: to determine whether we are alone in the universe. Methane, with its dual nature as both a biosignature and a geological artifact, embodies the central tension of this pursuit. It is a molecule that whispers of life's potential, yet warns of the perils of wishful thinking. To study it is to confront the limits of our knowledge and the vastness of what remains unknown. In this sense, methane is more than a scientific puzzle. It is a metaphor for the human condition, a reminder that our journey to understand the cosmos is as much about self-discovery as it is about exploration. If methane is the breath of life, then ozone is its guardian, a molecular sentinel that stands between a planet's fragile biosphere and the relentless fury of its star. While methane hints at the presence of life, ozone speaks to its survival, a protective layer woven from the threads of chemistry and physics that shields life from the lethal radiation of the cosmos. On Earth, ozone forms a fragile but vital barrier in the stratosphere, absorbing the majority of the sun's harmful ultraviolet (UV) rays and allowing life to flourish in the relative safety of the surface. This invisible shield is not merely a passive defense mechanism. It is a dynamic feature of a living planet, sustained by the continuous production of molecular oxygen (ozone) through photosynthesis. Without ozone, Earth would resemble Venus, a world scorched by radiation and devoid of the complex ecosystems that define our home. The transition from methane to ozone marks a shift in perspective, from the question of whether life exists to the question of how it persists. While methane offers tantalizing clues about the emergence of life, ozone reveals the conditions necessary for its endurance. Just as methane's presence requires a delicate balance between biological and geological processes, ozone's formation depends on a cascade of chemical reactions that only occur in the presence of life. The interplay between these two molecules, the one exhaled by life and the other forged by its byproducts, creates a feedback loop that stabilizes a planet's environment, ensuring that life has the time and space to evolve. In the search for habitable worlds, ozone becomes not just a biosignature but a litmus test for a planet's ability to sustain complex, long-lived ecosystems. As we turn our attention to ozone in the next segment, we will explore its role in planetary protection, its spectral fingerprints in the atmospheres of exoplanets, and the ways in which its presence or absence can inform our understanding of a world's potential to harbor life. Like methane, ozone is a molecule of contrasts, a poison in the lower atmosphere and a savior in the upper layers, a fleeting byproduct of life and a cornerstone of its survival. By tracing its story, we gain not only insight into the mechanics of habitability, but also a deeper appreciation for the intricate web of processes that make life possible. In the grand tapestry of the cosmos, ozone is a reminder that existence is not merely about beginnings, but about the enduring struggle to endure. Above the swirling blue and green tapestry of Earth, a nearly invisible layer of molecules drifts in the stratosphere, a fragile yet formidable barrier forged by the interplay of sunlight, chemistry, and time. This is the ozone layer, a shimmering veil of triatomic oxygen, O4, that guards life beneath it from the sun's most destructive energy. From the vantage point of a distant exoplanet, it might appear as nothing more than a faint spectral signature, a whisper of ultraviolet absorption in the spectrum of starlight. Yet to those who study the cosmos, this whisper carries profound meaning. ozone is not merely a chemical curiosity. It is a sentinel of planetary vitality, a fingerprint of dynamic chemistry, and perhaps even a herald of life itself. Imagine standing on a barren, airless world, exposed to the raw fury of stellar radiation. Without a shield, the ultraviolet rays would carve through organic molecules, like a sculptor's chisel, erasing the delicate scaffolding of life before it could assemble. But here, on Earth, the ozone layer acts as a cosmic guardian, intercepting high-energy photons that would otherwise sterilize the surface. It is a paradoxical phenomenon, a molecule born from the very sunlight it seeks to block, created when ultraviolet light splits ordinary diatomic oxygen, O2, into reactive atoms that then bind into O. This cycle of destruction and creation is a testament to the ingenuity of nature, a self-sustaining mechanism that balances the violent forces of the universe with the quiet persistence of chemistry. Yet ozone is not just a shield, it is a riddle. To an alien observer peering across the void, its presence might suggest a world teeming with life, or one on the brink of collapse. For scientists searching for habitable planets beyond our solar system, ozone serves as both a beacon and a caution. It hints at an oxygen-rich atmosphere, a prerequisite for complex biochemistry, but it also warns of extremes. An overabundance could signal a runaway greenhouse effect, a planet cooked by its own radiative imbalance. In this way, ozone becomes a symbol of cosmic duality, a reminder that survival in the universe often depends on delicate equilibria, and that even the most protective layers can conceal hidden dangers. To understand ozone's role in planetary habitability, one must first grasp the intricate dance of atoms and photons that gives it form. The story begins with molecular oxygen, O2, a byproduct of photosynthesis, which accumulates in Earth's atmosphere over eons. When ultraviolet radiation, particularly wavelengths shorter than 2040 nanometers, strikes these O2 molecules, it cleaves them into individual oxygen atoms. These highly reactive fragments do not remain solitary for long. They collide with neighboring O2 molecules, forming ozone O3, in a process known as the Chapman cycle. This cycle is not static. It is a continuous loop driven by the sun's relentless energy and the ceaseless motion of gas molecules in the stratosphere. What makes this process remarkable is its sensitivity to environmental conditions. Ozone formation peaks at altitudes of 10 to 50 kilometers, where temperatures and pressures allow the reaction to proceed efficiently. Too low, and the density of O2 is insufficient. Too high, and the molecules escape into space. The ozone layer is thus a product of precise planetary engineering, a balance of gravity, chemistry, and stellar distance. Even minor deviations in these parameters could render the layer ineffective, leaving a planet vulnerable to radiation, or trapping excessive heat in a suffocating greenhouse effect. This fragility underscores ozone's dual nature as both a shield and a warning. On Earth, it blocks approximately 97–99% of incoming ultraviolet UVB radiation, a range of wavelengths capable of damaging DNA and disrupting cellular functions. Without this protection, surface life as we know it would struggle to evolve beyond microscopic forms. Yet ozone's presence alone is not enough to guarantee habitability. Consider Venus, whose dense atmosphere contains trace amounts of ozone, but is otherwise a cauldron of sulfuric acid and scorching temperatures. Or Mars, where a thin, dry atmosphere allows unfiltered radiation to bombard the surface. These worlds demonstrate that ozone is only one piece of a far larger puzzle. Moreover, the concentration of ozone is influenced by atmospheric dynamics and human activity. On Earth, industrial emissions of chlorofluorocarbons, CFCs, once disrupted the ozone layer, creating seasonal holes over Antarctica. Though international efforts have curbed this damage, the incident highlights how easily a stable system can unravel. For exoplanets, similar perturbations, whether natural or artificial, could shift the balance from habitability to hostility. Thus, when astronomers detect ozone in a distant world's atmosphere, they must consider not only its abundance, but also its context, the planet's temperature profile, the presence of other gases, and the stability of its climate. The implications of ozone extend far beyond its immediate protective function. challenging our understanding of life's possibilities in the cosmos. Suppose a future mission detects a thick ozone layer on an exoplanet orbiting a sun-like star. At first glance, this might seem promising, a sign of abundant oxygen and active photochemistry. Yet such a discovery would demand scrutiny. Does the ozone coexist with other biosignatures, such as methane or nitrous oxide, which are typically produced by living organisms? Or is it the result of non-biological processes, such as volcanic outgassing or photodissociation of carbon dioxide? Distinguishing between these scenarios is a central challenge in the search for extraterrestrial life. Consider a hypothetical scenario: a planet with a dense ozone layer, but no detectable molecular oxygen. Such a world might initially appear lifeless, yet it could harbor an entirely different form of biochemistry. On Earth, ozone is a transient byproduct of oxygen-based respiration. But what if another planet sustains life through a chemistry that generates ozone independently? Perhaps its organisms thrive on a different energy source, such as hydrogen sulfide or ammonia, producing ozone as a secondary metabolite. Alternatively, the planet might host a prebiotic soup, where ozone forms abiotically, but facilitates the emergence of life through unknown pathways. These possibilities remind us that our search for habitable worlds must remain open to the unexpected. Even more intriguing is the idea that ozone could mask a planet's true nature. A thick stratospheric layer might obscure surface features or lower atmosphere gases, making it difficult to assess habitability. Imagine a world where ozone shields a scorching, toxic surface, a greenhouse oasis that appears temperate from afar but is inhospitable at ground level. Conversely, a planet with a thin ozone layer might expose its surface to radiation, but still support hardy extremophiles in subsurface oceans or shaded regions. These complexities underscore the limitations of remote sensing and the necessity of follow-up observations. On Earth, the history of ozone offers lessons for interpreting exoplanetary data. During the Great Oxidation Event around 2.4 billion years ago, rising oxygen levels led to the formation of a global ozone layer, fundamentally altering the planet's climate and biology. Early life forms likely struggled to adapt to this new shield, which both protected and constrained evolutionary trajectories. Similarly, the rise and fall of ozone concentrations on ancient Earth may have influenced the timing of major evolutionary milestones. By studying these historical shifts, scientists can better model how ozone interacts with planetary systems and what its presence might imply for alien worlds. Yet perhaps the most profound implication of ozone lies in its duality as a marker of both life and death. A world with an ozone layer might be a cradle of biodiversity or a graveyard cloaked in illusion. Detecting ozone without corroborating evidence, such as water vapor, methane, or signs of surface activity, risks falling into the trap of false positives. The lesson is clear: no single biosignature can confirm the presence of life. Instead, we must adopt a holistic approach, piecing together a mosaic of clues that reveal a planet's true character. If ozone is a shield woven from the fabric of chemistry, then water is the thread that binds life together. While the ozone layer filters out the sun's harsh rays, water serves as the universal solvent in which life's molecular machinery operates. On Earth, every drop of liquid water tells a story of habitability, from the primordial oceans that birthed the first microbes to the icy depths of hydrothermal vents that nurture extremophiles. In the search for alien life, water vapor in exoplanet atmospheres could be the next great clue, a telltale sign of liquid reservoirs hidden beneath alien skies. Yet water, like ozone, is not a simple indicator. A planet might possess water locked in frozen polar caps or trapped in deep underground aquifers, invisible to telescopes. Others might have surface conditions so extreme that any liquid water exists only transiently, flashing into steam under intense heat or freezing into ice under crushing cold. Deciphering these nuances requires not only technological precision, but also a willingness to imagine the myriad ways life might adapt. As we turn our gaze to the hunt for water vapor, we carry forward the same questions that have guided our exploration of ozone. What does the presence of a molecule truly signify? And how do we distinguish a world teeming with life from one playing a cosmic mimics game? In the next segment, we will delve into the methods by which scientists seek water's spectral signature in the atmospheres of distant worlds. We will explore how this search informs our understanding of habitability and how it might one day lead us to the first undeniable proof of life beyond Earth. For now, let us remember that ozone and water are not isolated phenomena. They are threads in a vast cosmic tapestry, each revealing a fragment of the universe's capacity to create, sustain, and perhaps transcend life as we know it. Imagine standing on the shore of an alien world, gazing at an endless ocean stretching beyond the horizon. On Earth, water defines life itself, covering 71% of our surface in a shimmering mosaic of blue. Yet, as we peer into the vastness of space, we are left with a profound question. Is water a rare jewel, adorning only our pale blue dot? Or does it cascade across distant planets in unseen abundance? The search for exoplanets has revealed a staggering diversity of worlds, many of which may harbor oceans beneath their veils of clouds, or deep in shadowed craters. Water, the universal solvent, is not just a substance, it is the liquid gold of life, a chemical cornerstone that shapes geology, climate, and the very possibility of biology. But how do we know if such worlds exist beyond our solar system? How can we detect the faint whisper of water vapor in the atmospheres of planets light years away? And what does it mean for the story of life in the cosmos if we find them? These questions anchor us in the intersection of science and wonder, where every drop of water detected in a distant sky becomes a beacon of hope for humanity's eternal quest to find kinship in the stars. The universe, after all, is a master alchemist. From the fiery crucibles of dying stars to the icy depths of molecular clouds, water is forged in abundance. Hydrogen and oxygen, two of the most plentiful elements in the cosmos, combine in the cold dark of interstellar space, forming molecules that drift through time like stardust. When planetary systems coalesce, these building blocks rain down onto nascent worlds, sculpting landscapes and birthing oceans. Yet the presence of water alone is not destiny. It is a promise, yes, but also a riddle. Does a planet with a thick, steamy atmosphere conceal an endless sea beneath its clouds? Or is it a frozen desert, its waters locked in glacial chains? To answer these riddles, we must first understand how to read the signs of water across the void. This is the challenge and the triumph of modern astrophysics, to decode the spectral fingerprints of water vapor, to peer through the haze of distant skies, and to glimpse the hidden oceans that might cradle life in forms we cannot yet imagine. As we embark on this journey, let us remember that water is more than a mere ingredient. It is a storyteller. Every molecule carries echoes of its origins, every droplet a history of cosmic migration. The hunt for water worlds is not simply a search for habitability. It is a quest to unravel the threads connecting the birth of stars, the evolution of planets, and the fragile dance of life itself. In the following sections, we will explore the tools and theories that allow us to detect water in alien atmospheres, examine the paradoxes of planets drowning in oceans or shrouded in steam, and confront the delicate balance required for life to thrive. Along the way, we will discover that the quest for water is as much about understanding ourselves as it is about exploring the cosmos. After all, in the end, we are made of the same stuff as the stars, and water is the bridge between them. To detect water in the atmospheres of exoplanets, astronomers wield a tool as ancient as the stars themselves: light. Infrared spectroscopy, a technique rooted in the quantum mechanics of molecular bonds, allows us to dissect the chemical signatures of distant worlds. Every molecule, including water vapor, absorbs light at specific wavelengths, creating a unique pattern of absorption lines in a spectrum. By analyzing the light that filters through an exoplanet's atmosphere during a transit, when the planet passes in front of its host star, scientists can identify these spectral fingerprints, revealing the presence of water vapor, methane, carbon dioxide, and other gases. This method has become a cornerstone of exoplanetary science, transforming the search for habitable worlds from speculation into data-driven inquiry. Consider the case of a super-Earth, a class of planets with masses between Earth and Neptune. These worlds are often enshrouded in thick atmospheres, their surfaces cloaked in clouds that obscure direct observation. Yet, even in these murky conditions, water vapor can betray its existence. When a super-Earth transits its star, the starlight dims slightly, and the planet's atmosphere imprints its chemical signature on the light. If water vapor is present, it absorbs certain wavelengths of infrared light, leaving telltale gaps in the spectrum. Instruments like the James Webb Space Telescope, JWST, with its advanced near-infrared spectrograph, NIR-SPEC, are designed to detect these subtle variations with unprecedented precision. The process is akin to listening for whispers in a storm, challenging, but not impossible. However, the detection of water vapor is far from a simple task. Atmospheric interference, such as clouds or high-altitude aerosols, can obscure the signal, masking the true composition of a planet's air. Additionally, the distance from a star plays a critical role in determining the state of water. A super-Earth orbiting close to its star might possess a scalding atmosphere of steam, with surface temperatures hot enough to boil oceans into vapor. Conversely, a similar planet farther out could host frozen seas or cryovolcanoes spewing water-rich plumes. The habitable zone, a region where temperatures allow liquid water to persist, is thus a dynamic target, shifting with the luminosity of the star and the atmospheric properties of the planet. Beyond the habitable zone lie worlds of extremes. Some exoplanets, known as hot Jupiters, orbit so closely to their stars that their daysides are bathed in molten heat, while their nightsides plunge into freezing darkness. Others, like the icy giants of the outer solar system, harbor subsurface oceans trapped beneath kilometers of ice. The diversity of these environments underscores the complexity of water's role in planetary evolution. A planet's history, its formation, migration, and interactions with its star shapes the distribution and state of water over billions of years. For scientists, the challenge lies in untangling these variables to determine whether a detected water signal heralds a temperate oasis or a desolate wasteland. The implications of these discoveries extend beyond the detection of water itself. The presence of water vapor in an exoplanet's atmosphere can indicate active geological or hydrological cycles, processes that redistribute heat and nutrients essential for sustaining life. On Earth, the water cycle drives weather patterns, erosion, and the movement of continents, all of which are intertwined with the planet's long-term habitability. If similar cycles exist on other worlds, they could provide clues about the potential for life to emerge and evolve. Yet, as we will explore in the next section, the presence of water does not guarantee habitability or even life. The story of water worlds is one of balance, where too little or too much can tip the scales towards sterility. Water is a paradoxical element. In the right measure, it is the elixir of life. In excess, it may become a prison. This duality is central to the study of water worlds, planets where oceans dominate the surface, potentially submerging any landmasses into the abyss. Such worlds could harbor vast unbroken seas teeming with microbial life, but they also face a fundamental dilemma: the absence of exposed rock. On Earth, the interaction between water and land is a dynamic engine of change. Rivers carve valleys, glaciers grind mountains, and tectonic plates collide and recycle the planet's crust. These processes are not merely geological, they are biological. Plate tectonics, for instance, regulate Earth's climate by cycling carbon dioxide between the atmosphere and the mantle, a process crucial for maintaining stable temperatures over eons. Without land to erode and replenish the oceans with nutrients, a water world risks stagnation. Could such a planet sustain the kind of chemical complexity required for life to evolve beyond the microbial stage? This question has sparked intense debate among astrobiologists. Some argue that a moderate amount of water, enough to form oceans but not so much that it drowns the continents, is a prerequisite for advanced life. They point to the role of continental weathering in delivering phosphorus and other essential elements to marine ecosystems. Phosphorus, a key component of DNA and ATP, the energy currency of cells, is largely sequestered in terrestrial rocks. If a planet lacks exposed land, its oceans may become nutrient deprived, limiting the potential for complex ecosystems. Furthermore, the absence of tectonic activity on a water world could could hinder the regulation of greenhouse gases like carbon dioxide, leading to runaway climate shifts. Imagine a planet where volcanic eruptions, the primary source of atmospheric CO2, are absent because the crust is entirely submerged. Without a mechanism to release this gas, the planet might gradually cool, locking its oceans in a permanent ice age. Yet the idea that water worlds are inherently inhospitable is not universally accepted. Recent simulations suggest that even in the absence of land, tidal forces from a planet's moon or its star could generate internal heat, driving convection currents and potentially mimicking the effects of plate tectonics. Additionally, some researchers propose that life could adapt to extreme nutrient scarcity, evolving strategies to extract trace elements from the deep sea or utilizing alternative biochemistries. The discovery of extremophiles on Earth, organisms thriving in hydrothermal vents, acidic lakes and frozen tundras, demonstrates the resilience of life in the face of adversity. Perhaps then a water world is not a dead planet, but a cradle for a life form so alien to our own that it defies our current understanding. Complicating matters further is the concept of the Goldilocks water zone, the hypothetical range of water abundance, where a planet is neither too dry nor too wet for life. This idea draws parallels to the habitable zone's temperature-based constraints, but introduces a new dimension of complexity. Determining this sweet spot requires modeling not just the physical properties of water, but also the interplay between planetary geology, atmospheric dynamics, and biochemical processes. For example, a planet with a thin veneer of water might experience frequent droughts, destabilizing ecosystems. Conversely, a planet with a global ocean might lack the mineral-rich sediments that foster biodiversity. The challenge for scientists is to distinguish between these scenarios using remote observations, a task that demands increasingly sophisticated instruments and interdisciplinary collaboration. Even if we resolve the question of water's optimal quantity, another uncertainty remains: the nature of the water itself. On Earth, liquid water exists due to the delicate balance of pressure, temperature, and salinity. A water world with a highly saline ocean might resemble the briny lakes of Mars, where life, if it exists, would face extreme osmotic stress. Alternatively, a planet with a low salinity ocean might struggle to dissolve vital minerals, creating a different set of biochemical hurdles. The presence of exotic solvents, such as ammonia or methane, further complicates the picture, as they could support life under conditions we have yet to fully comprehend. Ultimately, the exploration of water worlds forces us to confront the limits of our knowledge. Are we assuming too much when we equate water with habitability? Is our Earth-centric view of life blinding us to possibilities that defy intuition? As we refine our models and gather more data, we inch closer to answers, but the journey itself is a testament to the universe's capacity to surprise us. The next step in this quest is to scrutinize the signals we interpret as signs of life, recognizing that even the clearest evidence can sometimes be misleading. This leads us to a sobering realization: the search for life beyond Earth is not just about finding water, but about distinguishing truth from illusion in the cosmic theater. As we turn our gaze from the shimmering oceans of distant worlds to the delicate art of interpretation, we encounter a sobering reality. The line between life and non-life is perilously thin. Even if we detect water vapor, oxygen, or methane in an exoplanet's atmosphere, these so-called biosignatures are not infallible indicators of life. Oxygen, for instance, is a double-edged sword. On Earth, it is a byproduct of photosynthesis, a hallmark of abundant life. Yet, in the absence of life, oxygen can accumulate through abiotic processes, such as the photodissociation of water vapor by ultraviolet radiation. A planet orbiting a young, active star might thus display oxygen in its atmosphere, not because of algae or forests, but because of a relentless bombardment of stellar flares tearing apart water molecules. Similarly, methane, a potent greenhouse gas and a product of microbial metabolism, can be generated by geological activity, such as serpentinization, a process where water reacts with certain types of rock to produce hydrogen and methane. These false positives underscore the need for caution in our interpretations. The universe is a master of mimicry. capable of producing chemical signatures that mirror those of life without requiring a single cell to exist. To complicate matters further, some combinations of gases, known as biosignature gases, may only appear in the presence of life. For example, the simultaneous presence of methane and oxygen in a stable equilibrium is highly unlikely without a biological source, as these gases react with each other over time. However, verifying such combinations requires precise measurements and an understanding of the planet's atmospheric chemistry, a feat that pushes the boundaries of current technology. As we venture deeper into the analysis of exoplanetary atmospheres, we must adopt a mindset of skepticism tempered with curiosity. The next segment will delve into the intricate web of challenges posed by false positives, examining how non-biological processes can masquerade as signs of life, and what strategies scientists employ to differentiate between the two. The quest for life beyond Earth is not merely a search for water worlds. It is a test of our ability to discern meaning in the noise of the cosmos. In the vast, silent expanse of the cosmos, where stars ignite and die in cycles older than time itself, humanity has always sought to decode the universe's most tantalizing question: are we alone? Science, our most trusted lens, has long been the architect of this quest, building bridges between observation and meaning. Yet, the very tool that promises clarity often whispers in riddles. The universe is a master of misdirection, its secrets cloaked in phenomena that mimic the signatures of life. A planet glowing with the faint shimmer of oxygen-rich air might seem to breathe with the pulse of biology, yet it could be nothing more than a chemical mirage, a false positive, a cosmic illusion born of natural forces. This paradox lies at the heart of our exploration, the tension between evidence and interpretation. Just as the ancients mistook the shifting canals of Mars for the work of intelligent beings, modern astronomers now grapple with the possibility that the same hubris might cloud their judgment. The James Webb Space Telescope, with its golden eyes peering into the atmospheres of distant worlds, may soon detect molecular signatures that hint at life. But how do we distinguish between the breath of a living world and the echoes of chemistry? The answer lies not in a single clue, but in the interplay of context, probability, and the relentless pursuit of truth. Consider the case of Venus, once thought to harbor oceans and alien forests beneath its thick clouds. Early observations suggested a wet, temperate world, a potential cradle for life. Decades later, we learned it was a furnace, its surface scorched by runaway greenhouse effect. Similarly, the methane plumes detected on Mars in 2018 sparked wild speculation about microbial life, only for follow-up studies to reveal that geological processes could just as easily explain the signal. These stories remind us that the universe is both generous and deceptive, offering breadcrumbs that may lead either to revelation or ruin. As we venture further into the cosmic dark, the stakes grow higher. Each new discovery carries the weight of human longing, the yearning to find kinship among the stars. Yet in this search, we must remain vigilant against the siren call of false hope. The line between life and chemistry is not etched in stone, but drawn in shifting sands. To navigate this terrain, we must embrace humility, recognizing that the universe's truths are not ours to impose, but to uncover with patience and precision. The universe is a chemist's laboratory, where elements dance in reactions that defy intuition. On Earth, life's presence is often betrayed by its byproducts, oxygen, methane, and other molecules that serve as telltale signs of biology. But these same chemicals can arise through purely abiotic means, their origins rooted in the raw energy of geology and stellar radiation. Understanding these processes is essential to unraveling the enigma of false positives, for they reveal the universe's uncanny ability to mimic life without its presence. Take ozone, a molecule that once seemed synonymous with habitability. On Earth, ozone forms in the stratosphere when ultraviolet light splits oxygen molecules, allowing them to recombine into 3-atom clusters. This protective layer shields life from harmful radiation and serves as a proxy for oxygen's abundance, a biosignature in its own right. Yet ozone can also emerge from non-biological sources. Lightning, for instance, generates fleeting bursts of ozone during electrical discharges, while volcanic activity can release chlorine compounds that catalyze its formation. On an airless moon like Europa, ice particles struck by radiation from Jupiter's magnetic field may create ozone-like molecules, their spectral signatures indistinguishable from those of a living world. In such cases, the presence of ozone becomes a double-edged sword, a marker of atmospheric complexity that could either whisper of life or scream of chemistry alone. Methane presents an equally confounding tale. On Earth, 90% of the gas stems from microbial metabolism. Its steady emission a testament to life's persistence. Yet methane is also the product of geological alchemy. Deep within a planet's crust, heat and pressure can fracture carbon-containing minerals, liberating methane through serpentinization, a process observed in Earth's oceanic ridges and potentially active on Mars. Volcanic eruptions, too, can spew methane into the atmosphere, their plumes carrying the gas high enough to escape detection by ground-based instruments. Even colder worlds like Titan host methane cycles driven by liquid hydrocarbons and cryovolcanism, creating a methane-rich atmosphere that mimics the conditions of a biologically active planet. Without additional context, such as the presence of other gases or isotopic ratios, it is nearly impossible to determine whether methane's source is life or a mere accident of physics. Oxygen, perhaps the most iconic biosignature, holds its own contradictions. The Great Oxidation Event 2.4 billion years ago transformed Earth's atmosphere, turning it blue with breathable air. Today, oxygen is produced almost exclusively by photosynthesis, its abundance a direct consequence of life's dominance. But on a lifeless world, oxygen can still accumulate through abiotic processes. Consider a planet orbiting a young volatile star, whose high-energy radiation tears apart water vapor in the upper atmosphere. The hydrogen escapes into space, leaving behind oxygen, a ghost of a chemical reaction that bears no relation to biology. Such a scenario, though rare, is not implausible. In fact, recent simulations suggest that planets with thin atmospheres and active UV fluxes could amass oxygen without the need for life. The danger lies in assuming that any oxygen-rich atmosphere must host life, ignoring the possibility that it is merely a relic of a star's fury. These examples underscore a critical principle in astrobiology. Context is everything. A single molecule, however promising, cannot stand alone as proof of life. Instead, scientists must piece together a mosaic of evidence, considering a planet's geology, climate, and stellar environment to discern whether a biosignature is genuine or a clever trick of chemistry. This task is complicated by the sheer diversity of planetary systems. A planet orbiting a red dwarf star, for instance, faces tidal locking and intense stellar flares, conditions that could drive unique chemical pathways. Another world with a molten core might sustain volcanic activity for eons, masking or mimicking the signatures of life. Each system demands a bespoke approach, one that balances caution with curiosity. Yet, even with these considerations, the challenge remains daunting. The universe is vast, and the permutations of chemistry are infinite. For every confirmed biosignature, there may be 10 false leads waiting in the shadows. The trick is to recognize that ambiguity is not failure but the price of exploration. In the end, the quest to identify life beyond Earth is not just about finding answers, it is about refining the questions we ask and the frameworks we use to seek truth in a universe that thrives on uncertainty. The specter of false positives looms large over the search for extraterrestrial life, casting a shadow not only on scientific discovery, but on the very philosophy of exploration. Imagine a future where a distant exoplanet is hailed as the first confirmed abode of alien life, its oxygen-rich atmosphere and methane plumes celebrated as irrefutable proof of biology. Years later, a follow-up mission reveals that the methane was the product of deep-seated geological activity, and the oxygen, a byproduct of photodissociation. The initial excitement gives way to disillusionment, and the scientific community is left grappling with the fallout. Such a scenario underscores the profound consequences of misinterpretation, not just for the credibility of astrobiology, but for the trajectory of human ambition in the cosmos. One of the gravest risks of false positives is the potential to delay or derail the discovery of genuine life. Resources, both financial and intellectual, are finite, and a premature declaration of life, even if later disproven, could divert attention from more promising targets. Consider the case of the Viking landers on Mars in the 1970s, which conducted experiments designed to detect microbial metabolism. While ambiguous results led to decades of debate, the initial enthusiasm for a positive finding spurred significant investment in Mars exploration. Had the Viking team incorrectly interpreted their data as conclusive evidence of life, subsequent missions might have focused on confirming that hypothesis rather than expanding the search to other worlds. The lesson is clear: a false positive, even when corrected, can create inertia in the scientific process, anchoring efforts to a singular narrative at the expense of broader exploration. Equally troubling is the existential weight of false positives in the context of humanity's place in the universe. If we mistakenly declare a planet to be inhabited, we risk reinforcing the notion that Earth is unique, that life is a cosmic rarity. This conclusion could stifle the imagination and innovation required to search for life in unconventional forms or locations. For instance, if we assume that only planets with Earth-like atmospheres can host life, we might overlook the potential for microbial ecosystems in the subsurface oceans of icy moons like Enceladus or Europa. False positives could thus become a self-fulfilling prophecy, narrowing our definitions of habitability and limiting our vision of the cosmos. To mitigate these risks, the scientific community has turned to a strategy known as the biosignature cocktail, the idea that no single molecule or phenomenon should be used in isolation to infer life. Instead, researchers advocate for the simultaneous detection of multiple complementary biosignatures, each of which would reinforce the likelihood of biological activity. For example, the coexistence of oxygen and methane in an atmosphere is considered a strong biosignature because these two gases rapidly destroy each other unless continuously replenished by life. Similarly, the presence of complex organic molecules such as amino acids or nucleotides, alongside isotopic anomalies indicative of biological fractionation, provides a more robust case for life. By requiring multiple lines of evidence, scientists can reduce the chances of a false positive arising from a single coincidental process. Independent verification further strengthens this approach. Just as the Hubble Space Telescope's early images of the universe were refined by the James Webb Space Telescope's deeper infrared vision, future missions will likely rely on a suite of instruments to corroborate findings. Spectroscopic analysis, for instance, can identify the molecular composition of an exoplanet's atmosphere, while direct imaging might reveal surface features suggestive of biological activity, such as vegetation or seasonal changes. Ground-based observatories, space telescopes, and eventually in-situ probes will form a network of confirmation, ensuring that no single instrument or technique shoulders the burden of proof. Beyond the technical measures, the philosophical implications of false positives demand reflection. The search for life is not merely a scientific endeavor. It is a deeply human pursuit, shaped by our hopes, fears, and cultural narratives. A false positive could inadvertently influence public perception, fueling either excessive optimism or conversely skepticism toward astrobiology as a field. In a world already polarized by misinformation, the line between scientific discovery and hype is perilously thin. Thus, transparency and communication are paramount. Scientists must not only share their findings, but also contextualize their uncertainties, educating the public about the complexities of interpreting data in the face of cosmic ambiguity. Ultimately, the pursuit of life beyond Earth is a journey fraught with both wonder and humility. False positives serve as a reminder that the universe does not yield its secrets easily, and that our interpretations are always provisional. Yet, in this uncertainty lies the essence of discovery, the willingness to revise our understanding, to question our assumptions, and to embrace the unknown. As we continue to peer into the abyss, we must remember that the greatest revelations often begin with a simple act of doubt, a recognition that the truth, whatever it may be, is worth the effort to find. If the cosmos is a stage of endless possibilities, then Earth is both the playwright and the prologue. Our home planet, with its boiling hydrothermal vents, scalding acid lakes, and subterranean labyrinths of microbial life, offers a blueprint for understanding the resilience of biology and the ways in which life can blur the line between the extraordinary and the mundane. To refine our search for extraterrestrial life, we must first turn inward, studying the very organisms that thrive in Earth's harshest environments. These extremophiles, as they are called, challenge our conventional notions of habitability and provide invaluable insights into the diverse strategies life employs to survive. Consider the hydrothermal vents of the deep ocean, where superheated water spews from the seafloor, rich in chemicals like hydrogen sulfide. Here, entire ecosystems flourish in perpetual darkness, sustained not by sunlight, but by chemosynthetic bacteria that convert inorganic molecules into energy. These communities, discovered in the 1970s, revolutionized our understanding of life's potential, suggesting that similar environments such as the subsurface oceans of Europa or Enceladus might harbor life. By studying the metabolic pathways of vent-dwelling microbes, scientists can identify biosignatures that might persist in the alien chemistries of other worlds. Similarly, the hyper-arid Atacama Desert in Chile, one of the driest places on Earth, hosts microbes that extract moisture from the air using specialized proteins. These organisms, buried inches beneath the surface to avoid desiccation and UV radiation, offer a model for life that might exist on Mars or the icy moons of the outer solar system. Their survival strategies, such as producing antifreeze proteins or entering cryptobiotic states during droughts, inform our search for life in similarly harsh environments where traditional biosignatures might be obscured by the planet's extreme conditions. Even more astonishing are the extremophiles found in Earth's most violent settings. The Yellowstone National Park, with its geysers and hot springs, harbors thermophilic archaea that thrive at temperatures exceeding 80 Celsius. These microbes, capable of surviving in pH levels ranging from highly acidic to alkaline, demonstrate that life is not confined to the narrow band of conditions we associate with Earth's surface. Their existence suggests that life on other planets might persist in environments far removed from our own, relying on chemical gradients rather than sunlight for sustenance. By cataloging these terrestrial analogues, astrobiologists can develop a more nuanced framework for identifying life beyond Earth. For instance, the detection of complex organic molecules in the plumes of Enceladus's subsurface ocean could be interpreted through the lens of Earth's extremophiles, revealing patterns of biological activity that align with known biochemical processes. Likewise, the discovery of perchlorates on Mars, compounds that can both preserve organic material and support microbial metabolism, highlights the importance of understanding Earth's analogues before drawing conclusions about extraterrestrial life. This inward gaze is not merely a preparatory step, but a philosophical necessity. Earth is our only confirmed example of life, and its diversity serves as both a constraint and a guide. By embracing the full spectrum of life's adaptability, we expand our capacity to recognize its manifestations in the cosmos. As we prepare to explore the next segment of our journey, how Earth's extremes inform the search for life, we carry with us the knowledge that the universe's secrets are often written in the margins, in the hidden corners of our own world. The answers we seek may not lie in the stars themselves, but in the lessons etched into the very fabric of life on Earth. Beneath the scalding surface of Earth's most hostile environments, life persists in forms so alien they challenge our very definitions of survival. Picture a world where the air is thick with sulfuric acid, the ground is a seething cauldron of molten rock, and temperatures rival those of industrial ovens. Yet, in these crucibles of chaos, organisms not only endure, they flourish. These are the extremophiles, Earth's unassuming pioneers of the impossible. Their existence whispers a profound truth. Life is not a fragile candle flickering in a narrow window of conditions, but a wildfire that leaps across the most inhospitable landscapes. If life exists elsewhere in the cosmos, it will likely bear little resemblance to the lush greenery of a rainforest or the serene symmetry of coral reefs. Instead, it may mirror the tenacity of extremophiles, organisms that thrive in acid, radiation, boiling vents, and frozen deserts. By studying these earthly survivors, we unlock a new lexicon for the search for extraterrestrial life, one where habitability is measured not by the presence of water alone, but by the audacity of adaptation itself. The universe, vast and indifferent, offers no guarantees. Planets orbit stars in elliptical orbits that ebb and flow with extremes of heat and cold. Moons are battered by radiation and buried under kilometers of ice. Exoplanets may possess atmospheres laced with toxins or crushed under crushing gravity. Yet, here on Earth, life has carved out niches in every conceivable corner of this planet, from the hydrothermal vents, spewing superheated chemicals miles beneath the ocean, to the salt-crusted pools of Antarctica's dry valleys. Extremophiles remind us that life's playbook is far richer than we ever imagined. These organisms do not merely survive against the odds, they rewrite the rules. Their existence compels us to reconsider what constitutes a habitable world, both on Earth and beyond. In the shadow of these microbial marvels, the cosmos reveals itself as a tapestry of possibilities where life's potential is not confined to the familiar, but stretches into the sublime and the bizarre. To understand extremophiles, we must first abandon the notion that life requires a temperate, Earth-like environment. These organisms thrive in conditions that would sterilize most known species. Consider the hydrothermal vents of the deep sea, where temperatures exceed 400 Celsius and pressures crush submarines. Here, archaea and bacteria form the foundation of entire ecosystems, drawing energy not from sunlight, but from the chemical reactions of hydrogen sulfide and methane spewing from the Earth's crust. These microbes perform chemosynthesis, a process akin to photosynthesis, but one that relies on inorganic molecules rather than chlorophyll. By converting toxic gases into usable energy, they create a self-sustaining web of life, independent of the sun's influence. Such adaptations are not mere curiosities, they are blueprints for survival in environments where conventional biology would fail. Other extremophiles inhabit the opposite end of the spectrum, in the McMurdo dry valleys of Antarctica, where liquid water is scarce and temperatures plummet to -89. Certain bacteria encase themselves in antifreeze proteins to prevent cellular collapse. Meanwhile, in the hyper-arid Atacama Desert, where rainfall is a myth, lichens extract moisture from the air through a symbiotic relationship with fungi. Even more astonishing are the Deinococcus radiodurans bacteria, which can withstand doses of radiation 1,000 times higher than lethal to humans. These organisms repair their DNA with such efficiency that they appear almost invincible, as if evolution had sculpted them for the apocalypse. What unites these disparate life forms is their ability to exploit resources others deem unusable. In the absence of sunlight, they harness geothermal energy. In the absence of water, they extract it from the air. In the face of radiation, they evolve molecular shields. These strategies are not isolated phenomena, but the result of billions of years of evolutionary experimentation. Over eons, natural selection has sculpted extremophiles into paragons of adaptability. Each species a testament to life's relentless ingenuity. Their biochemical pathways, from unique enzymes to novel metabolic cycles, represent a hidden reservoir of biological innovation, one that could revolutionize fields ranging from biotechnology to medicine. Yet the true significance of extremophiles lies not in their utility to humanity, but in their capacity to redefine the boundaries of life itself. For centuries, biologists assumed that life required a narrow range of conditions: moderate temperatures, neutral pH levels, and an abundance of water. Extremophiles shattered this paradigm, proving that life can flourish in conditions once considered sterile. This revelation has profound implications for astrobiology, the branch of science dedicated to searching for life beyond Earth. If organisms can thrive in Earth's most inhospitable regions, then the search for extraterrestrial life cannot be limited to planets that mirror our own. It must expand to include worlds where temperatures swing from blistering to frigid, where atmospheres are thick with ammonia or methane, and where sunlight is replaced by the glow of geothermal activity. The implications of extremophiles extend far beyond Earth, casting a new light on the search for life in the cosmos. Consider Jupiter's moon Europa, where a global ocean lies hidden beneath an icy shell. The absence of sunlight in this subterranean world might seem inhospitable, but extremophiles offer a compelling counterpoint. On Earth, hydrothermal vents in the deep ocean support entire ecosystems without solar energy, relying instead on chemical gradients. If similar vents exist beneath Europa's ice, they could provide the necessary conditions for microbial life. Similarly, Saturn's moon, Enceladus, which ejects plumes of water vapor and organic molecules from its south pole, may harbor analogous environments. The presence of salts and silica particles in these plumes suggests hydrothermal activity, hinting at a possible habitat for chemosynthetic organisms. Even beyond the icy moons of the outer solar system, extremophiles challenge our assumptions about habitability. Take Venus, whose surface is a hellish landscape of volcanic rock and temperatures hot enough to melt lead. While the surface is clearly uninhabitable, the upper atmosphere of Venus presents an intriguing anomaly. At an altitude of 50 kilometers, temperatures and pressures approximate those of Earth. Recent studies have detected traces of phosphine gas, a compound associated with biological activity in this layer. Could extremophiles adapted to high acidity and low oxygen exist as airborne microorganisms in Venus's clouds? Such a scenario, though speculative, aligns with the precedents set by Earth's extremophiles, which have shown that life can persist in environments previously deemed impossible. The lesson from Earth's extremophiles is clear: life adapts to its surroundings, not the other way around. This adaptability reshapes our approach to detecting biosignatures, the chemical markers that indicate the presence of life. Traditionally, scientists have focused on oxygen, a byproduct of photosynthesis, as a primary biosignature. However, extremophiles suggest that other compounds such as sulfur dioxide, ammonia, or even methane could serve as equally valid indicators. For instance, on Mars, the detection of methane in the atmosphere has sparked debate about its origin. While geological processes could explain the gas, its presence in seasonal fluctuations raises the possibility of microbial life metabolizing it in underground reservoirs. Similarly, on Titan, Saturn's largest moon, lakes of liquid methane and ethane suggest a chemistry alien to Earth. Yet extremophiles teach us that life can exploit a wide array of energy sources. Could methanogens, microbes that produce methane as waste, exist in Titan's frigid seas, utilizing acetylene or hydrogen as fuel? This redefinition of habitability also expands the scope of our search. The traditional Goldilocks zone, or the region around a star where liquid water can exist, is now seen as too restrictive. Moons like Europa and Enceladus lie far from their stars yet host subsurface oceans. Exoplanets with thick atmospheres rich in carbon dioxide or nitrogen might sustain life through alternative biochemistries. Even rogue planets, worlds ejected from their solar systems and adrift in interstellar space, could harbor life in their cores, sustained by geothermal heat. The discovery of extremophiles on Earth has thus become a cornerstone of astrobiology, providing a framework to envision life in forms we have yet to imagine. Moreover, extremophiles compel us to rethink the timeline of life's emergence. On Earth, the earliest evidence of life dates back 3.5 billion years, shortly after the planet cooled from its molten infancy. These primordial organisms were likely extremophiles, thriving in the volatile conditions of early Earth. If life arose so quickly under such harsh circumstances, it suggests that life may be a common, perhaps inevitable, outcome of planetary evolution. This perspective shifts the focus of astrobiology from the question, is there life out there, to where isn't life out there? Every exoplanet, every moon, every asteroid becomes a potential cradle of life, waiting to be explored. As we stand on the precipice of this new era in astrobiology, the study of extremophiles serves as both a compass and a catalyst. These resilient organisms have expanded our understanding of life's potential, but they also highlight the limitations of our current tools and methodologies. To detect life beyond Earth, we must refine our instruments and broaden our criteria for habitability. This leads us to the next frontier, the analysis of exoplanet atmospheres. Recent advancements in technology have brought this goal within reach. Instruments like the James Webb Space Telescope, JWST, allow scientists to peer into the atmospheres of distant worlds, identifying the faint chemical signatures of potential biospheres. By studying the light absorbed and emitted by exoplanets, researchers can detect gases such as oxygen, methane, and water vapor, key indicators of habitability. Yet, as the study of extremophiles has shown, life may manifest in ways we have yet to anticipate. Future missions may need to scan for less familiar compounds, such as hydrogen sulfide or dimethyl sulfide, which could signal microbial activity in extreme environments. The journey ahead is as much philosophical as it is scientific. Just as extremophiles have reshaped our perception of life's resilience, the search for exoplanet biosignatures will challenge our preconceptions about what constitutes a living world. As we refine our techniques and expand our gaze, we move closer to answering one of humanity's oldest questions: are we alone in the universe? The answer may lie not in the familiar, but in the wild cards of life's boundless creativity. This script blends scientific rigor with poetic reflection, emphasizing the transformative role of extremophiles in redefining our search for extraterrestrial life. Each section builds upon the last, weaving a narrative that bridges Earth's resilience with the cosmos' untapped possibilities. In the vast uncharted wilderness of the cosmos, where the faint whispers of distant worlds echo across billions of years, humanity has always sought to pierce the veil of the unknown. The launch of the James Webb Space Telescope, JWST, in 2021 marked a seismic shift in this ancient quest. Perched at the edge of the solar system, 1,000,000 miles from Earth, this observatory is more than a machine. It is a testament to human ingenuity, a bridge between our fragile blue planet and the infinite. Unlike its predecessors, which captured the universe in visible light or X-rays, the JWST gazes into the infrared spectrum, where the secrets of the cosmos lie hidden. Its primary mirror, a segmented marvel of gold-coated beryllium, collects photons that have traveled eons through the void, carrying stories of star formation, planetary birth, and the chemical fingerprints of alien skies. This revolution is not merely about sharper images or brighter galaxies. It is about sniffing out the invisible, the intangible, the faint traces of oxygen, water, and carbon dioxide that might one day reveal whether life exists beyond Earth. In this era of discovery, the JWST stands as both a sentinel and a storyteller, unraveling the tapestry of the universe one spectral line at a time. The journey of the JWST began not in the cold vacuum of space, but in the fevered imaginations of scientists who dared to dream of a telescope capable of peering into the cradle of the cosmos. Designed to succeed the legendary Hubble Space Telescope, the JWST was conceived with a singular purpose: to observe the first galaxies and chart the evolution of the universe from its earliest moments. Yet its capabilities extend far beyond this grand ambition. With its ability to detect infrared light, the telescope can peer through the dusty shrouds of star-forming regions and into the atmospheres of exoplanets, those elusive worlds orbiting distant stars. Each observation is a collision of physics and philosophy, a moment where the laws of nature meet the questions that have haunted humankind since antiquity. As the JWST unfolds its delicate web of mirrors and instruments, it becomes clear that this is no ordinary instrument of science. It is a vessel for wonder, a tool that transforms the abstract into the tangible, the distant into the familiar. At the heart of the JWST's revolutionary power lies its ability to decode the atmospheres of exoplanets, a task that demands both technical brilliance and a profound understanding of the universe's most subtle signals. The key to this feat is infrared spectroscopy, a technique that analyzes how light interacts with matter. When a planet passes in front of its host star, a phenomenon known as a transit, some of the starlight filters through the planet's atmosphere. Different molecules absorb light at specific wavelengths, leaving behind a unique fingerprint. By comparing the light before and after the transit, the JWST can identify the presence of gases such as water vapor, carbon dioxide, methane, and even the telltale haze of organic particles. This process, though deceptively simple in concept, requires extraordinary precision. The telescope's instruments, including the near-infrared spectrograph (NIR-SPEC) and the mid-infrared instrument MIRI, are engineered to detect changes in brightness measured in parts per million, an achievement akin to spotting a firefly's flicker against the glare of a lighthouse. What makes the JWST uniquely suited for this task is its sensitivity to infrared wavelengths, which are longer than visible light and can penetrate the obscuring dust that blankets many regions of the cosmos. This capability is critical when studying small rocky exoplanets, whose atmospheres are notoriously difficult to analyze, unlike gas giants like Jupiter, which have thick, easily detectable clouds. Terrestrial planets present a fainter signal, requiring the JWST's unparalleled resolution to tease out their secrets. The telescope's cryogenic cooling system ensures that its detectors remain at temperatures near absolute zero, minimizing thermal noise and allowing it to capture the faintest glimmers of starlight filtered through alien skies. Moreover, the JWST's location at the second Lagrange point, motion L2, a gravitationally stable position far from Earth's heat and interference, provides an unobstructed view of the cosmos. Here, shielded by a tennis court-sized sunshield, the telescope operates in a near-perfect thermal environment, ensuring the clarity of its observations. This technological prowess is not merely an exercise in engineering. It is a gateway to understanding the conditions that shape worlds. By mapping the molecular composition of exoplanet atmospheres, the JWST can infer surface temperatures, the presence of liquid water, and even the potential for complex chemistry. For instance, the detection of water vapor suggests the existence of oceans or clouds, while carbon dioxide hints at active geological processes or greenhouse effects. Methane, a molecule often associated with biological activity, could one day serve as a biosignature, a clue that life may exist beyond Earth. Yet the JWST's true power lies in its ability to ask questions that no previous instrument could answer. Where Hubble glimpsed the shadows of distant planets, the JWST illuminates their substance, revealing the intricate dance of atoms and molecules that define their essence. Since its deployment, the JWST has begun transforming our understanding of exoplanets, turning the abstract into the concrete and the hypothetical into the measurable. Among its early targets were hot Jupiters, giant planets that orbit perilously close to their stars, and super-Earths, rocky worlds with masses between Earth and Neptune. These celestial bodies, once mere data points in the vast catalogue of exoplanets, now emerge as vibrant laboratories of planetary science. The detection of water vapor in the atmosphere of WASP-39b, a hot Jupiter located 700 light-years from Earth, was a milestone that demonstrated the telescope's ability to dissect the chemical makeup of alien worlds. Similarly, the analysis of K2-18b, a super-Earth in the habitable zone of its star, revealed the presence of water vapor, hydrogen, and helium, findings that sparked global excitement and speculation about the possibility of life in its clouds. These discoveries are not isolated events, but part of a broader effort to map the diversity of planetary environments, from the hellish infernos of molten lava planets to the frigid, methane-rich worlds of the outer systems. Yet the true frontier lies in the study of temperate, Earth-like exoplanets, where the conditions for life may be most favorable. The JWST's future targets include the 7 planets of the TRAPPIST-1 system, a star system just 40 light-years away that has captivated astronomers since its discovery in 2016. 3 of these planets, TRAPPIST-1e, F, and G, reside within the habitable zone, where temperatures could allow liquid water to exist on their surfaces. The JWST will scrutinize their atmospheres for signs of oxygen, nitrogen, and other biologically relevant gases, seeking patterns that deviate from the sterile norms observed in non-living worlds. However, this endeavor is fraught with challenges. Earth-like planets are smaller and dimmer than their gas giant counterparts, making their atmospheric signals even fainter. Moreover, the presence of clouds or thick hazes can obscure the underlying chemistry, requiring sophisticated models to disentangle the true composition. These obstacles underscore the complexity of the search for extraterrestrial life, a quest that demands not only cutting-edge technology, but also a willingness to confront the unknown with humility and patience. Even as the JWST pushes the boundaries of current knowledge, it serves as a harbinger of future breakthroughs. The telescope's observations will inform the design of next-generation instruments, such as the proposed Large Ultraviolet Optical Infrared Surveyor, LUVOIR, and the Habitable Exoplanet Imaging Mission, HABEX, which aim to directly image Earth-like planets and analyze their atmospheres in greater detail. In the coming decades, these missions may one day capture the first direct image of a distant world teeming with life, a moment that would redefine humanity's place in the cosmos. Until then, The JWST continues its silent vigil, collecting photons from the furthest reaches of the universe and translating them into data that speak of worlds both alien and familiar. Each observation is a thread in the tapestry of cosmic history, weaving together the story of how planets form, evolve, and perhaps, in rare and precious cases, give rise to life. As the JWST peers ever deeper into the alien atmospheres of distant exoplanets, its insights inevitably draw our gaze back to the familiar realms of our own solar system. The same principles of spectroscopy and atmospheric and anospheric analysis that illuminate the mysteries of exoplanets can be applied to the worlds we have long known but never fully understood. Venus, with its crushing atmosphere of carbon dioxide and sulfuric acid clouds, offers a cautionary tale of runaway greenhouse effect. Mars, once a warm and wet planet, now cloaked in a thin, cold envelope of carbon dioxide, holds clues to the fragility of habitability. Even the icy moons of Jupiter and Saturn, with their subsurface oceans and potential for hydrothermal activity, invite comparisons to the enigmatic exoplanets the JWST studies. By refining our techniques on these nearby worlds, we sharpen our tools for deciphering the more distant and elusive targets beyond our solar system. This reciprocal relationship between exploration and introspection underscores the interconnectedness of all scientific inquiry. The same spectral lines that reveal water on an exoplanet also appear in the frosty regolith of Europa or the plumes of Enceladus. The models we develop to interpret the chemistry of alien skies must account for the complexities of Earth's own atmosphere, where ozone, methane, and aerosols play intricate roles in shaping climate and weather. In this way, the study of exoplanets becomes a mirror for understanding our own planet's past, present, and future. As we continue to unravel the cosmic puzzle piece by piece, we find that the answers we seek in the stars are often rooted in the lessons of our own backyard. With this foundation laid, the journey to comprehend the universe and our place within it moves forward, guided by the twin lights of curiosity and discovery. Before venturing into the vast uncharted territories of exoplanets, humanity turns its gaze inward to the familiar yet enigmatic realm of our own solar system. This celestial neighborhood, a cradle of worlds orbiting the sun, offers a treasure trove of lessons encoded in their surfaces, atmospheres, and histories. Each planet, moon, and asteroid is a testament to the dynamic forces that shape planetary systems, a symphony of chaos and order where collisions, volcanic activity, and atmospheric evolution have sculpted diverse environments over billions of years. By studying these cosmic siblings, we gain not only a deeper understanding of planetary formation, but also a framework for deciphering the mysteries of distant worlds. Take Venus, for instance, a planet shrouded in perpetual clouds of sulfuric acid, with surface temperatures hot enough to melt lead. Its thick atmosphere, dominated by carbon dioxide, traps heat in a runaway greenhouse effect that has transformed it into a furnace. Mars, in stark contrast, is a barren desert, its once water-rich past now reduced to frozen ice caps and dry riverbeds carved by ancient floods. And then there is Titan, Saturn's largest moon, whose methane seas and complex organic chemistry whisper of chemical processes that may echo those of early Earth. These worlds, though alien in their extremes, serve as both cautionary tales and blueprints for life. They remind us that habitability is not a binary state, but a spectrum shaped by intricate interactions between geology, climate, and chemistry. In this cosmic backyard, every planet tells a story, one that guides our search for life beyond the stars. Yet the allure of these worlds lies not merely in their individual peculiarities, but in the questions they provoke. What caused Venus to become a hellscape, while Earth remained temperate? Why did Mars lose its magnetic field and atmosphere, leaving it vulnerable to the harshness of space? How does Titan, with its methane cycles and prebiotic chemistry, challenge our definitions of habitability? These questions form the bedrock of comparative planetology, a discipline that seeks to unravel the threads connecting planetary evolution across time and space. As we peer into the mirror of our solar system, we begin to glimpse the possibilities and perils that await us in the wider universe. At its core, comparative planetology is the art of reading the geological and atmospheric records of planets to reconstruct their evolutionary paths. By analyzing the similarities and differences among worlds, scientists piece together the mechanisms that govern planetary behavior. Venus, often dubbed Earth's twin, due to its comparable size and mass, serves as a stark reminder of how small variations in initial conditions can lead to vastly divergent fates. While Earth's atmosphere retains a delicate balance of nitrogen and oxygen, Venus's atmosphere is a crushing 96% carbon dioxide, with surface pressures 92 times that of Earth. This suffocating envelope of gas creates a runaway greenhouse effect, where solar radiation is absorbed and re-radiated back toward the surface, trapping heat in an unrelenting cycle. Temperatures soar to nearly 470 across, hot enough to vaporize lead and resurface the planet repeatedly through massive volcanic eruptions. The absence of liquid water and tectonic activity further isolates Venus from Earth, highlighting the fragility of planetary habitability. Mars, on the other hand, presents a different puzzle. Once thought to be a cold, dry world, recent discoveries reveal a planet that once harbored rivers, lakes, and perhaps even an ocean. Its thin atmosphere, composed primarily of carbon dioxide, with trace amounts of nitrogen and argon, cannot retain heat effectively, resulting in average temperatures of -60°C. Yet evidence suggests that Mars was warmer and wetter in its youth, with a global magnetic field that shielded it from the solar wind. The gradual disappearance of this magnetic field allowed the atmosphere to erode over millions of years, stripping away volatiles and rendering the surface inhospitable. Today, water exists only as ice at the poles and in subsurface deposits, locked in a state of dormancy. Studying Mars's transformation from a potentially habitable world to a frozen wasteland underscores the precarious nature of planetary stability and the role of external influences, such as solar radiation and orbital dynamics, in shaping a planet's destiny. Titan, Saturn's enigmatic moon, adds another layer of complexity to this cosmic narrative. With a diameter larger than Mercury and a dense nitrogen-rich atmosphere laced with methane, Titan is the only moon in the solar system with a substantial atmosphere and stable surface liquids. Its methane cycle mirrors Earth's hydrological cycle, complete with rain, rivers, and lakes. But instead of water, it is methane and ethane that flow across its frigid landscape. The presence of complex organic molecules, such as tholins, raises tantalizing questions about prebiotic chemistry and the potential for alternative biochemistries. Titan's environment, though alien, challenges the notion that life must resemble Earth's informal function. Here, under the shadow of Saturn's rings, the building blocks of life may be assembling in ways that defy terrestrial intuition. Through these comparisons, comparative planetology reveals that planetary evolution is not a linear process, but a chaotic dance of chance and necessity. Factors such as distance from the Sun, internal heat, atmospheric composition, and impact history all play roles in determining a world's trajectory. By cataloging these variables, scientists construct models that simulate planetary development, allowing them to predict how similar or dissimilar exoplanets might behave. For instance, a super-Earth orbiting close to a red dwarf star might experience tidal locking, creating extreme temperature gradients and atmospheric collapse. A Neptune-like planet with a thick hydrogen-helium envelope could trap volatile compounds, preventing the emergence of surface conditions conducive to life. These insights, drawn from our own cosmic neighborhood, provide a critical foundation for interpreting the burgeoning data on exoplanets. The lessons gleaned from our solar system compel us to abandon the assumption that Earth is the universal standard for habitability. While Earth's conditions, liquid water, moderate temperatures, and a protective magnetic field, are undeniably hospitable, they represent only one possible configuration in the vast tapestry of planetary diversity. Comparative planetology teaches us that life, if it exists elsewhere, may thrive in environments that seem utterly inhospitable by terrestrial standards. Consider the case of Venus, where a dense carbon dioxide atmosphere creates a hellish inferno. On first glance, such a world appears devoid of potential for life. Yet recent studies suggest that high-altitude regions in Venus's atmosphere might harbor pockets of cooler temperatures and trace amounts of water vapor, conditions that could theoretically support microbial life in aerial niches. Similarly, the subsurface oceans of icy moons like Europa and Enceladus challenge traditional notions of habitability by demonstrating that liquid water can persist beneath kilometers of ice, sustained by tidal heating and chemical reactions rather than direct sunlight. These revelations underscore the importance of expanding our search criteria beyond Earth analogical conditions. For example, an exoplanet with a dense CO2 atmosphere might initially appear as a dead world, but its internal dynamics could give rise to unique chemical cycles capable of sustaining life. Conversely, a planet with ammonia or methane-based solvents might develop biochemistries entirely unlike those on Earth, relying on different metabolic pathways and molecular structures. Such possibilities demand a shift in perspective, from seeking exact replicas of Earth to embracing the full spectrum of chemical and environmental diversity. This paradigm shift is not merely academic, it directly influences the design of observational instruments and the interpretation of exoplanetary data. Spectroscopic analyses of exoplanet atmospheres, for instance, must account for the presence of non-terrestrial gases and the potential signatures of exotic biospheres. Moreover, comparative planetology highlights the role of planetary scale in determining habitability. Giant planets like Jupiter and Saturn, with their deep atmospheres and intense radiation fields, are unlikely hosts for life as we know it. However, their moons, particularly those with subsurface oceans, emerge as promising candidates. Io, for instance, is a geologically active world with volcanic plumes driven by tidal flexing, while Ganymede and Callisto possess ice-covered oceans that may contain more water than all of Earth's oceans combined. These moons exemplify how habitability can arise in indirect ways, dependent on factors such as orbital resonance, internal heat generation, and the availability of energy sources like hydrothermal vents. When applied to exoplanets, this logic suggests that habitable zones may extend beyond the traditional Goldilocks region and include moons orbiting gas giants within the habitable zone of their stars. Another critical implication of comparative planetology lies in the recognition of transient habitability. Many planets in our solar system, including Mars and Venus, were once more hospitable than they are today. This raises the possibility that exoplanets currently deemed uninhabitable might have been habitable in the past, or will become so in the future. The concept of paleohabitability challenges the static view of habitable worlds, emphasizing that a planet's suitability for life can evolve over time. For example, a planet with a thin atmosphere and no liquid water today might have had a thicker atmosphere and abundant water billions of years ago, during a period of intense geological activity. Alternatively, a planet with a runaway greenhouse effect now might cool down in the future if its star dims or if atmospheric processes change. These scenarios complicate the search for life, as they require distinguishing between current and past habitability and considering the likelihood of life having emerged, thrived, and possibly vanished over eons. Perhaps most profoundly, comparative planetology underscores the need to guard against anthropocentric biases in the search for extraterrestrial life. Human-centric assumptions, such as the belief that life requires liquid water, oxygen, and carbon-based molecules, may limit our ability to recognize truly alien forms of life. The discovery of extremophiles on Earth, organisms that thrive in boiling hot springs, deep-sea hydrothermal vents, and acidic lakes, has already expanded our understanding of life's resilience. Yet these examples still conform to Earth's biochemical framework. To imagine life beyond this framework, we must draw inspiration from the diversity of planetary conditions in our own solar system. Titan's methane lakes, for instance, suggest that life might utilize non-aqueous solvents, while the high-pressure environments of deep Earth analogs hint at the potential for life in supercritical fluids. By studying these extremes, we begin to appreciate that the biosphere of another world might operate on principles that seem as foreign to us as the concept of flight once seemed to ground-bound creatures. As we stand on the precipice of understanding our solar system's lessons, a new question emerges. What if life's journey does not end with the boundaries of planets themselves? For centuries, humanity has imagined life as a phenomenon tethered to solid worlds, thriving in soil, oceans, or atmospheres. Yet the very forces that shape planets, collisions, volcanic activity, and the ceaseless churn of cosmic debris suggest that life's story might be far more expansive. Could the seeds of life in the form of microscopic organisms or organic molecules travel across the void, carried by asteroids, comets, or even the solar wind? This radical idea, known as Panspermia, challenges the notion that life arises independently on each suitable world. Instead, it proposes that life may be a shared inheritance of the galaxy, distributed by the very material that birthed the stars and planets. To explore this possibility, we must venture beyond the confines of planetary surfaces and into the vast, seemingly empty spaces between them. Here, in the dark expanse of interstellar and interplanetary mediums, lie the remnants of shattered worlds, the frozen relics of ancient collisions, and the building blocks of new ones. Comets, for instance, are icy wanderers that preserve primordial material from the solar nebula, their nuclei rich in organic compounds and water. Some of these comets may have delivered the essential ingredients for life to Earth billions of years ago, seeding our oceans with amino acids and other prebiotic chemicals. Similarly, meteorites, fragments of asteroids that have fallen to Earth, often contain carbon-based molecules that hint at the presence of life's precursors in the asteroid belt. If these materials can survive the violent journey through space and the fiery descent through a planet's atmosphere, what other secrets do they carry? The implications of such a perspective are staggering. If life can hitch a ride on these cosmic couriers, it is not merely a product of individual planets but a phenomenon woven into the fabric of the universe itself. The same processes that scattered debris from planetary collisions could, in principle, transport life between worlds, perhaps even between star systems. Theoretical models suggest that high-speed impacts could eject material from one planet's surface into space, where it might drift for millennia before settling onto another. While the probability of such an event leading to the transfer of viable life is debated, the mere possibility reshapes our understanding of life's origins. Are we alone in the universe, or are we simply the latest chapter in a saga that began long before Earth's formation? This transition from planetary habitability to interstellar life transfer invites us to reimagine the cosmos, not as a collection of isolated worlds, but as a dynamic, interconnected web of exchange. Just as the planets of our solar system have influenced one another through gravitational tugs and material exchanges, so too might life transcend the boundaries of individual stars. In this vision, the search for life becomes not just a quest to find it on distant exoplanets, but to trace its origins across the galactic stage. What if the answer lies not in the conditions of a single planet, but in the intricate dance of matter and energy that spans the heavens? With this question in mind, we turn our attention to the possibility of life's migration across the stars. By examining the mechanisms that could enable such a journey, whether through natural processes or the ingenuity of advanced civilizations, we open a new frontier in the exploration of life's place in the universe. The next segment will delve into the theoretical frameworks and observational evidence that support the idea of interstellar life transfer, inviting us to consider a cosmos where life is not a rare anomaly, but a shared legacy of the stars. In the vast, star-dappled expanse of the universe, where galaxies spiral like celestial whirlpools and nebulae glow with the hues of creation itself, lies a question that has haunted humanity since the dawn of thought. Where did we come from? For centuries, the answer was rooted in Earth, a planet cradling the primordial soup of amino acids, lightning, and volcanic heat. Yet, in recent decades, a radical hypothesis has emerged, one that reimagines the birthplace of life as not a single world, but the cosmos itself. Panspermia, the notion that life may have hitched a ride across the stars, challenges the comforting idea that Earth is the sole cradle of existence. It suggests that microbes, resilient and ancient, may have traveled aboard comets, asteroids, or even interstellar dust, seeding planets with the raw ingredients of life. This idea transforms our understanding of biology from a planetary phenomenon to a universal one, painting a picture of life as a traveler, not an accident. To grasp the magnitude of panspermia is to envision a universe teeming with possibility, where life is not a solitary spark, but a flickering flame carried on the winds of cosmic storms. Imagine a comet, its surface popped with ice and rock, drifting silently through the void. Eons ago, this icy wanderer might have collided with Earth, releasing a payload of organic compounds into the young planet's turbulent seas, or perhaps a Martian meteorite, ejected during a cataclysmic impact, carried microscopic passengers to our shores, their genetic code waiting patiently to awaken. These scenarios, once dismissed as science fiction, now occupy the forefront of astrobiology, blending astronomy, geology, and microbiology into a quest to unravel life's origins. Panspermia does not merely propose that life began in space. It suggests that life is a cosmic constant, a force that transcends the boundaries of worlds. In this narrative, Earth becomes not a unique oasis but a stop along a galactic highway, where life's journey began long before the first cells formed in Earth's oceans. The allure of panspermia lies in its audacity. It dares to look beyond the confines of our planet and consider that life's story is written in the stars. This idea invites us to reimagine ourselves not as isolated beings, but as members of a vast interconnected family stretching across the cosmos. As we peer deeper into the night sky, we are no longer mere observers, but participants in a grand cosmic drama, one where the seeds of life may have been sown by the very same forces that shaped the planets and stars. To understand how life might travel across the cosmos, we must first confront the harsh realities of space. A vacuum devoid of air, temperatures ranging from scorching heat near the sun to the frigid cold of interstellar voids, and relentless radiation, all seem inhospitable to life, and yet nature has a way of defying expectations. Microbes, some of Earth's hardiest inhabitants, possess extraordinary resilience, capable of surviving in environments that would obliterate most known organisms. These extremophiles thrive in boiling hydrothermal vents, acidic hot springs, and the sub-zero deserts of Antarctica. Could they endure the unforgiving conditions of space? The answer, increasingly supported by scientific experimentation, appears to be yes. Consider the process by which life might escape Earth and venture into the stars. Cataclysmic events such as asteroid impacts or volcanic eruptions could hurl debris into space at velocities sufficient to break free from Earth's gravity. Within these ejected fragments, microbes might find refuge in tiny cracks and crevices, shielded from the worst of space's brutality. Experiments conducted aboard the International Space Station have demonstrated that certain bacteria, such as Deinococcus radiodurans, can survive exposure to cosmic radiation and extreme temperatures for extended periods. Similarly, tardigrades or water bears have endured the vacuum of space for days, entering a cryptobiotic state known as tune formation, where their metabolism slows to nearly undetectable levels. If these organisms can withstand such trials, it is conceivable that similar microbes could persist for millennia within the icy armor of a comet or asteroid. Once launched into space, these stowaways would face another challenge: the journey itself. The solar system is a dynamic, chaotic realm, where gravitational interactions between planets and moons could redirect trajectories. A rock carrying microbes might orbit the sun for millions of years before being captured by another world's gravity. Some scientists propose that Mars and Venus, in their early histories, may have exchanged material with Earth, creating a cosmic siblinghood, where life could have migrated between planets. Beyond the solar system, interstellar dust particles, microscopic grains, traveling at high speeds, might serve as vectors for biological material, though the feasibility of such transport remains speculative. Even if life could survive the journey, it must also endure the arrival. Upon impact with a new world, the energy released could sterilize the surrounding area, but if the microbes are embedded deep within a meteorite, they might remain unscathed. On a planet with liquid water and a stable environment, these travelers could awaken from their dormant slumber, beginning the slow, intricate dance of evolution. This scenario, though theoretically plausible, hinges on the assumption that life can exist in a dormant state for eons and then resume activity upon encountering favorable conditions. While no definitive evidence of such a mechanism exists, the discovery of ancient viable seeds on Earth, some germinating after centuries of dormancy, suggests that dormancy as a survival strategy is not implausible. Panspermia thus presents a compelling framework for understanding life's potential ubiquity in the universe. It posits that the building blocks of life, organic molecules, perhaps even primitive cells, are not confined to individual planets, but are instead distributed across the cosmos by the very forces that shape celestial bodies. This perspective shifts the focus from the origin of life to its dispersal, framing the universe as a vast interconnected web, where life's journey is as much about travel as it is about emergence. If panspermia is more than a hypothesis, it profoundly alters our perception of life's rarity and uniqueness. The notion that life is a cosmic constant, that it flows like a river through the interstellar void, implies that the universe is far more alive than previously imagined. Every planet with the right conditions, liquid water, chemical complexity, and a stable climate, could be a potential haven for life, seeded by the same cosmic courier that brought us into existence. In this vision, Earth is not an anomaly, but a node in a vast interplanetary network of biological exchange. The discovery of life on Mars, Europa, or Enceladus would no longer signal the presence of independent evolution, but rather the confirmation of a shared heritage. We would not be alone, but we would also not be strangers, we would be kin. This realization carries profound philosophical and existential weight. For millennia, humans have sought to define their significance in the universe, often placing themselves at the center of creation. Panspermia dismantles this anthropocentric worldview, revealing a cosmos where life is not a singular event, but a recurring theme. It suggests that the processes giving rise to life, whether through panspermia or spontaneous abiogenesis, are not Earth-specific, but universal laws etched into the fabric of reality. In this context, humanity's quest to explore the stars is not merely about discovery, but about reconnecting with our cosmic origins. Each mission to Mars or Europa becomes a pilgrimage to ancestral homelands, a search for the echoes of life's earliest journeys. The implications extend beyond biology into the realms of culture, ethics, and identity. If life is a shared inheritance, then the relationships between species and ecosystems on different worlds take on a new dimension. Protecting alien life would not be an act of altruism, but a duty to preserve our own lineage. Consider the ethical quandaries that arise when we encounter a microbial ecosystem on Mars. Should we prioritize contamination prevention to avoid introducing earthly microbes? Or should we study the Martian biosphere with the tools we currently possess, risking unintended consequences? Such dilemmas highlight the tension between scientific curiosity and responsible stewardship, a tension that grows sharper as we approach the day when we might confirm the existence of extraterrestrial life. Moreover, panspermia reshapes our understanding of evolution. If life's blueprint is carried across the stars, then evolutionary trees are not isolated, but intertwined, with branches stretching between planets. This perspective challenges the traditional view of evolution as a purely terrestrial process, suggesting instead that natural selection operates on a cosmic scale. Genes in this model are not just the products of Earth's history, but part of a larger interplanetary dialogue, where traits honed on one world might manifest on another. The implications for synthetic biology and genetic engineering are staggering. If life shares a common origin, then manipulating its code might require a global, even interplanetary consensus. Yet, the beauty of panspermia lies in its capacity to inspire awe. It paints a universe brimming with possibilities, where every asteroid is a time capsule and every comet a messenger. It invites us to see ourselves as part of a grand, ongoing experiment, one in which life is not a fragile accident, but a tenacious traveler, adapting to the ever-changing cosmos. This vision aligns with humanity's deepest yearnings for connection, for meaning, for a place in the infinite. As we continue to probe the stars, we are not only searching for life, but for the threads that bind us to the universe itself. As we stand on the precipice of uncovering life's cosmic origins, the ethical dimensions of our quest demand careful consideration. If panspermia reveals that life is a shared inheritance, then our actions in space become acts of profound consequence. Every sample collected from Mars, every probe sent to Europa, carries the weight of responsibility, not just to avoid contaminating alien environments, but to honor the legacy of life's interstellar journey. How do we balance the drive for discovery with the imperative to protect what we find? How do we navigate the moral complexities of encountering life that is in essence a mirror of ourselves? These questions mark the threshold of a new chapter in humanity's relationship with the cosmos. They challenge us to redefine what it means to be explorers, not as conquerors of the unknown, but as stewards of a shared legacy. The answers will shape not only the future of space exploration, but also the values that guide our civilization as we reach outward into the stars. With this in mind, the next segment invites us to grapple with the ethical frameworks that must accompany our cosmic endeavors, frameworks that recognize the sanctity of life, wherever it may be found. Beneath the velvet expanse of the night sky, where constellations trace the ancient paths of civilizations and distant galaxies swirl in silent symphony, humanity stands at the edge of an unprecedented threshold. For millennia, we have gazed upward, weaving myths and philosophies to explain the cosmos. Yet the discovery of even the simplest life beyond Earth, a single-celled organism clinging to the icy crust of Europa or the sulfuric winds of Venus, would shatter the boundaries of our self-imposed isolation. Such a revelation would not merely expand our scientific understanding, it would plunge us into a moral quagmire of staggering proportions. Would we dare to reach out to speak across the chasm of light years, risking the disruption of alien ecosystems? Would we risk contaminating fragile worlds with our own biological imprints, as careless as ancient explorers who unwittingly carried plagues to unspoiled continents? And perhaps most hauntingly, what responsibility do we bear toward life forms whose existence could dwarf our own in complexity or intelligence? These are not abstract speculations, but urgent questions that lie at the heart of our species' next great leap into the unknown. The universe, vast and indifferent, offers no guarantees, only possibilities, and with them, the weight of choice. The scientific community has long grappled with the practical and ethical challenges of interplanetary exploration. Planetary protection protocols, formalized by organizations such as NASA, the Committee on Space Research, COSPAR, serve as a bulwark against the unintended consequences of our curiosity. When robotic probes land on Mars or dive beneath the ice of Jupiter's moon Europa, they are scrubbed clean of terrestrial microbes, their surfaces baked in autoclaves and sealed in sterile chambers. These measures are not mere precautions. They are acknowledgements of our fragility. Earth's biosphere is a delicate tapestry, and the introduction of even the hardiest bacteria-resilient strains of Deinococcus radiodurans or Extremophiles adapted to boiling hot springs could irreversibly alter alien environments. Yet these protocols apply primarily to microbial life, a realm where contamination is a matter of biological survival rather than existential consequence. The stakes rise exponentially if we encounter intelligence. Imagine a signal intercepted from a distant star system, its patterns unmistakably artificial, a sequence of prime numbers, fractal geometries, or harmonic frequencies that defy natural explanation. The discovery of such a transmission would ignite a frenzy of scientific analysis and philosophical debate. Could we decode it without imposing our own cognitive biases? Could we respond without revealing vulnerabilities? The very act of communication introduces asymmetries of power and intent. Are we prepared to negotiate with beings whose motives we cannot fathom, whose technologies may eclipse our own by eons? Or worse, are we naive enough to believe that silence equates to safety? History teaches us that isolation is rarely absolute. Even the most remote tribes on Earth have been discovered, their cultures irrevocably altered by contact. In the cosmic arena, where the distances are measured in millennia and the variables are infinite, the ethical calculus becomes maddeningly complex. The ripple effects of discovering extraterrestrial life would extend far beyond laboratories and observatories, cascading through the very foundations of human society. Religion, which has long framed humanity as the pinnacle of creation, would face a reckoning. If life exists elsewhere, does it diminish the uniqueness of our spiritual narratives? or does it elevate them to a universal scale? Some faiths might adapt, reinterpreting sacred texts to accommodate a cosmos teeming with meaning. Others might resist, clinging to doctrines that place Earth at the center of divine attention. Politics, too, would fracture under the strain. The discovery of a habitable exoplanet might spark a scramble for resources, with nations vying to claim the right to colonize or exploit alien worlds. Could we avoid repeating the cycles of imperialism that have scarred our own history? Or would the allure of cosmic dominion prove irresistible? Identity, perhaps the most intimate of all, would be rewritten. If we find intelligence beyond Earth, we must ask, what does it mean to be human in a universe that no longer belongs solely to us? The search for biosignatures, gases like oxygen or methane in exoplanetary atmospheres, is not merely a scientific endeavor. It is a quest for reflection. We seek life because we seek ourselves, hoping to glimpse our origins in the mirror of the stars. Yet this pursuit carries a paradox. The more we learn about the cosmos, the smaller we become, and the larger our questions grow. The same technology that allows us to peer into the atmospheres of distant worlds also enables us to see the fragility of our own planet, a pale blue dot adrift in the void. In this duality lies both despair and hope, the despair of insignificance and the hope of connection. As we ponder these questions, the universe continues its silent expansion, indifferent to our struggles, yet alive with potential. Every star is a sun, burning with the same nuclear fire that birthed our own solar system. Every planet is a possibility, a canvas upon which the forces of chemistry and time might paint the faintest whisper of life. Our telescopes, now trained on distant exoplanets, are the first instruments of a grander inquiry, one that transcends science and enters the realm of philosophy, ethics, and art. The next segment will take us further along this journey, delving into the technologies and strategies that drive our search for cosmic companionship. But before we proceed, let us pause to consider the weight of our gaze. We are not mere observers. We are participants in a story still being written, a story in which the answers we seek may one day come from hands and minds unlike our own. The cosmos awaits, not with judgment but with the quiet patience of eternity.